a subtle wobbling in the light of B. It could be a sign of tugging from a planet's gravity. If a planet is there, it literally hugs its parent star, with an orbit that's even closer than Mercury is to our Sun. It's probably molten, with surface temperatures in excess of 1,000 degrees centigrade. Are there other planets far enough out for liquid water to flow? That prospect is the subject of intrigue in science and science fiction. Alpha Centauri is the fictional location of Polyphemus, a giant gas planet, and its moon Pandora from the movie Avatar. The year is 2154. Earth has been ruined by environmental catastrophe. Greedy prospectors board the hybrid fusion antimatter spaceship, Venture Star. They descend on an innocent hunter-gatherer people called the Na'vi. Could such a place exist this close to home? One problem with Alpha Centauri is that the orbits of A and B bring the stars as close as Saturn is to our Sun. This means that planets further out could have been pulled away and flung out into space. For this reason, Alpha Centauri was not a high priority for planet hunters. That is, until similar examples turned up, such as Kepler-16. 16b is a planet that orbits two stars, which in turn orbit each other. Or Gliese 667, a triple star system 22 light-years from Earth. 667c is a red dwarf, 1/3 the mass of our Sun, with 6 planets in its fold. 3 of them, small enough to be called super-Earths, orbit at a distance that could allow liquid water to flow on their surface. That opens the possibility that planets may have survived in the Alpha Centauri system. For now, that question is on hold. The orbits of Alpha Centauri A and B have brought them too close for astronomers to resolve the signal of a planet. When they move apart again, astronomers will have new tools at their disposal, including the James Webb Space Telescope, now set for launch in 2018. From a position 1,000,000 miles away from Earth, it will deploy a sun shield the size of a tennis court and a mirror over 21 feet wide. Astronomers will use this telescope with its infrared light detectors to discern the chemical composition of planetary atmospheres. Here are Alpha Centauri A and B, as seen by the Cassini spacecraft just above the rings of Saturn. Assuming it's worth the trip, you'd have to travel a distance 30,000 times the orbit of Saturn to reach them. Put another way, if Earth to Saturn is a meter, then Earth to Alpha Centauri is New York to Chicago. To put the journey into perspective, consider Voyager 2, now on its way out into the galaxy. After a series of gravitational assists from Jupiter and Saturn, the spacecraft is traveling at about 62,000 kilometers per hour. If it were headed in the right direction, it would need another 73,000 years to reach Alpha Centauri. The dream of traveling to other solar systems was forged by rocketeers a century ago. A Russian schoolteacher, Konstantin Tsiolkovsky, inspired generations of space visionaries with sophisticated ideas about multi-stage launch vehicles. He imagined the construction of space stations in Earth orbit and eventually permanent space colonies. Someday, he predicted, we'll evolve into a whole new species, Homo cosmicus. Since then, rocketry's greatest advances have centered on ways of containing explosive propellants and methods of maintaining stable flight at high speeds. The problem with chemical rockets is that they are just not very efficient.
3 engines up and ready. 3, 2, 1.
To reach the speed needed to escape Earth's gravity, 25,000 kilometers per hour, the space shuttle carried 15 times its weight in fuel. A NASA study showed that to send a shuttle-sized craft to Alpha Centauri in 900 years would take an unbelievable amount of fuel, 10 to the 137th kilograms worth. That's more than the entire visible universe. There are several promising advanced propulsion concepts on the drawing board, including fuel-efficient plasma engines, which accelerate a spacecraft gradually to high speeds. It won't get us to Alpha Centauri in anything close to a human lifespan. To go that far and that fast, a pre-Apollo project called Orion called for a series of controlled nuclear explosions to propel a spacecraft to high speeds. The project died amid concerns about the impact of nuclear explosions on the environment. Back in the 1970s, a group of scientists unveiled designs for Daedalus. This giant fusion-powered craft would have had to carry 50,000 pounds of fuel. The plan was to accelerate to 12% the speed of light and reach a nearby star in 50 years. Other plans have included ramjets with vast magnetic fields that scoop up a fuel supply of hydrogen ions, or solar sails powered by the solar wind and by lasers stationed along the way. Then there's the rocket of choice in science fiction, powered by the most potent fuel in nature, antimatter. In James Cameron's Avatar, a fusion antimatter hybrid engine powers a 1,500-meter-long spaceship. It makes the journey to Alpha Centauri in just 6 years. Antimatter consists of electrons and protons, but with their electrical charges reversed. Whenever it comes into contact with normal matter, the two annihilate each other in a ferocious blast of energy. Only trace amounts can be found in the universe today. For example, in the high-energy environments of black holes. It's so powerful that a mere 10,000th of a gram is about all it would take to send a spacecraft to Jupiter. Current designs for an antimatter drive use magnetic fields to isolate and channel the fuel. The idea is to merge a stream of protons with a stream of its antimatter opposite, antiprotons. A magnetic field pinches or compresses the combined streams into a narrow beam. Annihilation then produces an ultra-high energy laser that shoots out the back of the craft. That causes a recoil effect that pushes on the magnetic field produced by the beam and propels the craft forward. Antimatter can be produced on Earth in giant physics labs like the Large Hadron Collider. Here, scientists accelerate atoms to nearly the speed of light and blast them together to release their fundamental constituents. The yield is so small that the cost of producing just a gram's worth of antimatter would be upwards of $100 trillion. And the stuff is so volatile that storing more than a few atoms at a time remains a significant challenge. If specialized facilities were built, the cost could drop by one estimate to as low as $10 billion per gram. One idea would be to station an antimatter factory in space, powered by the 1 billion watts per kilometer delivered by the sun. Another is to harvest antimatter already produced in space. The idea is that cosmic rays, interacting with interstellar particles, send about a kilogram of antimatter flying into the solar system every second. Some of it has been shown to circulate in radiation belts that surround the Earth. Theoretically, it could be captured by a large magnetic scoop that sits in a high orbit above the planet. Short of traveling to another solar system, there may be good reasons to develop antimatter propulsion. An interim mission would speed beyond the orbit of Pluto, sending back close-up images of objects in the Kuiper Belt. A longer-distance probe could reveal new details about the Oort cloud, a vast realm of comets that envelops the solar system. Once out there, it could sample interstellar particles or deploy an interstellar telescope. To make it all the way to Alpha Centauri within 50 years, an antimatter probe would have to accelerate to around 10% the speed of light, over 100 million kilometers per hour. High velocity has its perils. At such speeds, even dust has enough mass to destroy the craft. A magnetic shield would be needed to clear the way. If it could be done, there may be other destinations to consider. At least 22 stars within 12 light-years of Earth. Any way you look at it, the first interstellar voyage will be a quantum leap for humanity. The urge to reach out to distant horizons, to climb the highest peak, is a vital part of human nature. But explorers of old set off not just because it was there. At times it was greed, hunger, fear, and despair that propelled them from their homelands and allowed them to endure their long journeys. What imperatives will send future generations into space? To the physicist Stephen Hawking, it's a question of survival. "I don't think the human race," he said, "will survive the next 1,000 years unless we spread into space. There are too many accidents that can befall life on a single planet." We can't foresee the impact of wars, social upheaval, or the course of human civilization in coming centuries. But an early context for the mission may be emerging now. On one hand, the technological advances that might make such a mission possible could revolutionize many other aspects of life on this planet. The ever-increasing number of transistors that can be placed inexpensively on a computer microchip has become a metaphor for the advance of technology. Some observers forecast a steep rise, even an acceleration, in the pace of invention and basic research, and for whole new solutions to the problems of energy, food production, health, and more. In addition, despite the daily drumbeat of violence and war, we are actually living in one of the most peaceful eras in human history. Over the centuries, the number of people killed in battle has steadily dropped as civilizations evolved. With 2 world wars, the 20th century was pretty bad, but the 19th was even worse. In terms of deaths per 100,000, from war, genocide, murder, and other factors, the world is relatively calm. On the other hand, major periods of scarcity and suffering may loom. The last century saw the world's population grow from less than 2 billion to nearly 7 billion today. It may reach 9 to 10 billion by the year 2040. According to a recent UN report, the world will have to produce 70% more food by the year 2050, and at least that much more energy to sustain its population. Simple, clean water in some regions is already extremely scarce. Now throw in environmental impacts like rising sea levels, or the spread of deserts linked to a gradually warming climate. No matter how you look at it, our world is changing in ways that will impact the way we live and relate to each other. Will technological advancements allow us to halt the degradation of our natural environments and increase the carrying capacity of our planet? Will we find ways to mitigate the effects of war, natural catastrophes, or political upheavals? The technology needed to launch a first interstellar mission is certainly decades away. The actual journey could take centuries. The mission will likely be designed to relay basic information on a world whose light we have studied intensively from afar. Back home, it will no doubt spur reflection on who and what we have become as a people, as a planet. As our cosmic emissary makes its way across the void, we on Earth will continue to struggle in our pursuits of happiness, prosperity, and mere survival. When it arrives, we'll scan the data for evidence of a world like our own, one that may harbor life. Will we come to explore and expand our knowledge, or to begin a long journey out into the uncertain reaches of the galaxy?
The year is 2154. Our planet has been ruined by environmental catastrophe. In the movie Avatar, greedy prospectors from Earth descend on the world of an ancient hunter-gatherer people named the Na'vi. Their home is a lush moon far beyond our solar system named Pandora. Could such a place exist? And could our technology and our appetite for exploration one day send us hurtling out to reach it? In fact, the supposed site of this fictional solar system is one of our most likely real interstellar targets, until a better destination turns up. Pandora orbits a fictional gas planet called Polyphemus. Its home is a real place, Alpha Centauri, the brightest star in the southern constellation of Centaurus. At 4.37 light-years away, it's part of the closest star system to our Sun. Alpha Centauri is actually two stars, A and B, one slightly larger and more luminous than our own Sun, the other slightly smaller. The two stars orbit one another, swinging in as close as Saturn is to our Sun, then back out to the distance of Pluto. This means that any outer planets in this system, anything beyond, say, the orbit of Mars, would likely have been pulled away by the companion and flung out into space. For this reason, Alpha Centauri was not high on planet hunters' lists, until they began studying a star 45 light-years away, called Gamma Cephei. It has a small companion star that goes around it every 76 years. Now it seems it also has at least one planet. That world is about the size of Jupiter, and it has planet hunters excited. Perhaps 2/3 of all the stars in our galaxy are in so-called binary relationships. That means there could be many more planets in our galaxy than astronomers once assumed. At least 3 teams are now conducting long-term studies of Alpha Centauri, searching for slight wobbles in the light of each companion star that could indicate the presence of planets. If they find a planet that passes in front of one of the stars, astronomers will begin intensive studies to find out what it's like. One of their most promising tools will be the James Webb Space Telescope, scheduled for launch in 2014 or 2015. From a position 1 million miles away from Earth, it will deploy a sun shield the size of a tennis court and a mirror over 21 feet wide. The largest space telescope ever built, it will offer an extraordinary new window into potential solar systems like Alpha Centauri. With its infrared light detectors, this telescope will be able to discern the chemical composition of a planet's atmosphere. And perhaps whether it harbors a moon like Pandora. One prominent planet hunter predicted that if a habitable world is found at Alpha Centauri, the planning for a space mission would begin immediately. Here's that star duo seen by the Cassini spacecraft, just above the rings of Saturn. To actually get to this pair of stars, you'd have to travel as far as the orbit of Saturn, then go another 30,000 times further. Or put another way, if the distance to Alpha Centauri is the equivalent of New York to Chicago, then Saturn would be just 1 meter away. So far, the immense distances have not stopped us from launching missions into deep space. In 1977, the twin Voyager spacecraft were each sent on their way aboard Titan III Centaur rockets. After a series of gravitational assists from the giant outer planets, the spacecraft are now flying out of the solar system at about 40,000 miles per hour. They're moving so quickly that they could each whip around Earth in just 45 minutes. Twice as fast as the International Space Station. Voyager 1 has now traveled over 110 astronomical units. That's 110 times the average distance between Earth and Sun, or about 10 billion miles. But don't hold your breath. If it was headed in the right direction, it would need another 73,000 years to travel the 273,000 astronomical units to Alpha Centauri. When it comes to space travel, we've yet to realize the dream forged by rocketeers a century ago. A Russian schoolteacher, Konstantin Tsiolkovsky, inspired generations of space visionaries with sophisticated ideas about multi-stage launch vehicles. He imagined the construction of space stations in Earth orbit, and eventually vast permanent space colonies. In time, he predicted, we'd evolve into a whole new species, Homo cosmicus. Since then, rocketry's greatest advances have centered on ways of containing explosive propellants and methods of maintaining stable flight at high speeds. The problem is that chemical rockets are just not efficient for long-distance space travel. To reach the speed needed to enter orbit around Earth, 17,500 miles per hour, the space shuttle must carry 15 times its weight in fuel. And that's efficient compared to some other rocket systems. And you'd need to be traveling more than 25,000 miles per hour to break free of Earth's orbit and go anywhere else. A NASA study showed that to send a space shuttle-sized craft to Alpha Centauri in 900 years would take an unbelievable amount of fuel, 10 to the 137th kilograms of rocket propellant. Suffice to say, it's more mass than is in the entire visible universe. While only a very tiny percentage of NASA's budget goes to advanced propulsion, there are some promising ideas on the drawing board. Rockets powered by nuclear fuel, or plasma, a supervolatile gas. Huge sails pushed along by the pressure of photons from the sun. Ion drives. But to reach Alpha Centauri within a human timescale, we'll have to go with the most potent fuel in nature that we currently know. It's the science fiction fuel of choice, antimatter. In James Cameron's Avatar, hybrid nuclear fusion and antimatter engines power a mile-long interstellar spaceship. At a speed of 670 million miles per hour, this vehicle makes the journey to Alpha Centauri in just 6 years. Antimatter really does exist, as the mirror image of the universe we know. It consists of electrons and protons, but with their electrical charges reversed. Whenever it comes into contact with normal matter, the two annihilate each other in a ferocious blast of energy. Large amounts of antimatter were created and destroyed in the fiery dawn of our universe, the Big Bang. But somehow, in one of the great mysteries in science, we were left with a universe whose visible substance is almost all normal matter. The universe still produces antimatter through powerful collisions, such as a jet from a black hole slamming into a cloud of gas. When matter and antimatter obliterate one another, they emit gamma radiation that we can then detect with instruments such as the Fermi Gamma-Ray Space Telescope. Fortunately, black holes aren't the only way to generate antimatter. In giant labs, like the Large Hadron Collider, scientists accelerate atoms to nearly the speed of light and blast them together to expose their fundamental constituents. Small amounts of antimatter can be made this way, but it's incredibly expensive. With a dedicated facility, the cost of producing it might come down far enough to produce usable amounts. And that's the hope of one researcher. Dr. Gerald Smith has been working for over a decade to find a way to trap this volatile substance and store it in isolation from the rest of the universe. Smith and his colleagues have designed a trap the size of a cigar case. It sits within a tank filled with liquid nitrogen and liquid helium, designed to cool it down to 270 degrees below zero. Once injected into this trap, antimatter particles are suspended by magnetic fields within a vacuum as empty as deepest space. But the problem is that anti-electrons, called positrons, tend to repel each other explosively. That makes it tough to store more than a few at a time. This team now believes it may have discovered a pathway to storing large amounts over longer periods of time. Their solution lies in combining positrons with electrons, forming an element called positronium. In theory, with the right magnetic fields, these electrically neutral atoms might be held indefinitely. When released under controlled conditions, ultra-high energy antimatter beams could turn out to be ideal cancer killers, or lead to revolutionary industrial applications. Or perhaps, one day, they could power long-distance spaceflight. It wouldn't take much. Antimatter is so potent that it defies common sense. A chunk the size of a small coin could propel the space shuttle into orbit. Smith estimates that once in low Earth orbit, a human mission to Mars would take as little as 10 milligrams worth. The basic idea of an antimatter rocket is simple. A beam of positrons is released into the engine core, where it annihilates the surface of a metal plate. That creates an explosion that propels the craft forward. Another design uses a sail. A cloud of antimatter particles reacts explosively to its surface, propelling it forward. Short of traveling to another solar system, there may be good reasons to contemplate developing antimatter propulsion. A preliminary mission would speed beyond the orbit of Pluto, sending back close-up images of dark planet-like objects that ring the solar system out in the Kuiper Belt. A longer-distance probe could reveal new details about the Oort cloud, a vast realm of comets that envelops the solar system. Once out there, it could sample particles that make up the interstellar medium, or send back unique data sets on dark matter, the invisible stuff that makes up the overwhelming portion of our universe. To make it all the way to Alpha Centauri within 50 years, an antimatter probe would have to gradually accelerate to around 10% the speed of light, That's 67 million miles per hour. It would then gradually decelerate as it approached its destination. At those speeds, hitting even a grain of dust could destroy the spacecraft, so it might be best to slow the journey down to a century or more. It's safe to assume for now that we would only send a probe to Alpha Centauri if we discovered a habitable world. There may be other choices in our solar neighborhood. They include Proxima Centauri, a red dwarf star 4.2 light-years away that may be gravitationally bound to Alpha Centauri. Beyond that, not quite 6 light-years away, is Barnard's star. Or there's Lalande 21185, a red dwarf 8.3 light-years away. We already know it has 2 Jupiter-sized planets. There are at least 22 stars within 12 light-years of Earth. And any way you look at it, the first interstellar voyage will be a quantum leap for humanity. The urge to reach out to distant horizons, to climb the highest peaks, to push ourselves past our perceived limits seems to be a vital part of what makes us human. Yet, explorers of old set off not just because it was there. At times it was greed, hunger, fear, or despair that propelled them outward from their homelands and allowed them to endure their long journeys. Whether we attempt to make this leap to the stars may come to depend on how we regard this planet. To the physicist Stephen Hawking, the journey is imperative. I don't think the human race, he said, will survive the next 1,000 years unless we spread into space. There are too many accidents that can befall life on a single planet. Indeed, we can't foresee the impact of wars, social upheaval, or the course of human civilization in coming centuries. But today, we can see the often conflicting trends that could one day propel us out into the interstellar void. On one hand, the technological advances that might make such a mission possible could revolutionize many other aspects of life on this planet. The ever-increasing rate at which numbers of transistors can be placed inexpensively on computer microchips has become a metaphor for the advance of all technologies in this century. From a few thousand transistors on the first printed circuits of the 1970s, computer chips now have billions etched onto their surfaces. Even that number could seem amazingly small in another few decades. Many observers forecast a steep rise, even an acceleration, in the pace of invention and basic research, and for whole new solutions to the problems of energy, food production, health, and more. On the other hand, major periods of scarcity may loom. In the 20th century, the world saw the largest increase in its human population, from less than 2 billion up to 6 billion. The world's population is now around 6.8 billion. It's expected to reach 9 to 10 billion by the year 2040, with the biggest gains in Asia and Africa. According to a recent UN report, the world will have to produce 70% more food by the year 2050, and at least that much more energy to sustain its population. The scarcity of just simple clean water in some regions is already frightening. Now throw in environmental impacts, like rising sea levels, or the spread of deserts linked to a gradually warming climate. The culprit, to most scientists, is rising emission of greenhouse gases like carbon dioxide since the start of the Industrial Revolution. This map charts rising temperature readings from the year 1885 through to the present. In some places they've gone up by as much as 2.5 degrees Fahrenheit. Computer models project the trend out to the end of this century. Depending upon population growth, energy use, and conservation, temperatures could rise anywhere from 2 to 11 degrees more. Will technological advancements allow us to halt the degradation of our natural environments and increase the carrying capacity of our planet? Will we find ways to mitigate the impacts of war, natural catastrophes, or political upheavals? No doubt, if or when we launch our first mission beyond this solar system, the occasion will spur reflection on who and what we have become as a people, as a planet, just as the first missions to the moon and our neighboring planets once did. At first, we'll send a probe designed to relay basic information on what's there. On a world
where objects have permanence. And we see cause, then effect. But a startling phenomenon is revealing that this is not how the universe works at the smallest scales of atoms and tiny particles. Albert Einstein argued it couldn't possibly be real.
Einstein was like a jack-in-the-box. Every day he'd pop up with a new challenge.
But after a century of disputes and discoveries,
the experiment is just beautiful.
We're using it to create revolutionary new technologies.
What we have here is a quantum playground.
We want to push this technology as far as possible.
It's perhaps the strangest concept in physics.
We're left with conclusions that make no sense whatsoever.
Yet it could be what forms the very fabric of our cosmos.
In the end, we just have this quantum mechanical world. There is no space anymore.
It's like being in Alice in Wonderland. Everything is possible.
Could it be real? It's Einstein's quantum riddle. Right now, on Nova.
Major funding for NOVA is provided by the following.
Intuitive micro-world of atoms and tiny particles that challenges our intuitive understanding of the world we see around us. It's known as quantum mechanics. This strange theory has enabled us to develop the remarkable technologies of our digital age. But it makes a very troubling prediction called quantum entanglement.
Entanglement is this very powerful but strange connection that exists between pairs of particles.
Even if they're very far apart, in a way they're always coordinated.
Nature's fundamental building blocks could be connected and influence each other instantaneously, as if the space between them doesn't exist. As if two objects can mirror each other without any apparent connection. Einstein called it spooky action at a distance. He rejected the idea and tried to prove it couldn't be real.
You could have situations where the cause and the effect happen at the same time.
But if entanglement isn't real, cutting-edge technologies could be in jeopardy.
Quantum computers, quantum encryption, they depend on entanglement being a fact in the world.
Underlying it all is a profound question. Do we live in Einstein's universe of common sense laws? Or a bizarre quantum reality that allows spooky connections across space and time? "300 miles off the coast of West Africa, on one of the Canary Islands, a team of physicists is setting up a remarkable experiment that will use almost the entire breadth of the universe to settle the question, Is the seemingly impossible phenomenon of quantum entanglement an illusion, or is it actually real? Leading the team is Anton Zeilinger.
So we are now going up the mountain towards the Roque de los Muchachos. So everything looks perfect today.
It's a precarious undertaking. They've got a short window on two of Europe's largest telescopes. Each one will simultaneously focus on a different quasar, an extremely distant galaxy emitting huge amounts of light from its core. This light will be used to control precise equipment that must be perfectly aligned to make measurements on tiny subatomic particles.
Okay.
And if that isn't tricky enough, the weather on the mountain is notoriously unpredictable. The team needs perfect conditions for the experiment to work.
In the end, it could be running smoothly, or there need to be a couple of decisions made, you know, in an excited state in the last instant.
With the experiment finally set up, the team takes their positions. David Kaiser has worked on this experiment with his colleagues Jason Galicchio and Andy Friedman for 4 years. Coordinating it all is Dominic Rausch. The experiment is his thesis project, and it's been years in the making. But as darkness falls, temperatures on the mountain begin to drop.
Ja, Sie haben unsere Nummer und wenn es besser wird, werden wir angerufen.
Okay. Okay, großartig.
Ciao.
Okay, there's bad news. They have been told to leave the William Herschel because the road will be so dangerous, too dangerous, so they have to go down now. Yeah.
The next day, the team prepares for another attempt. They verify the equipment hasn't been affected by the weather. But now, the air is thick with clouds.
Here's the humidity at the various telescopes, and you see the humidity is 100%. So as long as this lasts, we can't do much.
The teams at both telescopes wait. But the clouds don't clear. All the preparation has come to nothing. Time on these huge telescopes is precious, and theirs has run out. This ambitious test of quantum entanglement must wait. Why are physicists so determined to put this bizarre aspect of quantum mechanics to the ultimate test? To explore the beginning of the story, David Kaiser has come to Brussels, the city that Albert Einstein traveled to in 1927, to attend a meeting about a new theory that described the microworld of atoms and tiny particles, quantum mechanics.
Quantum mechanics is one of those amazing intellectual achievements in human history.
For the first time, scientists were able to probe a world that was until then quite invisible to us. Looking at the world at the scale of atoms, 1 million times smaller than the width of a human hair.
One way to think about the scales is that if you take an everyday object, like a soccer ball, and you enlarge that soccer ball so that actually you can see the individual atoms. You roughly have to make it the size of the Earth. And then move into that planet. Then you are in the world of atoms and particles.
It was the nature of fundamental particles which make up the world we see around us that Einstein had come to Brussels to discuss. And it was here that Einstein entered into a heated debate that would lead to the discovery of quantum entanglement. A concept that would trouble him for the rest of his life. David Kaiser has come to the place where it all began.
This is the original Solvay Institute building. Beautiful, grand building. And this is the place back in October 1927 where the 5th Solvay conference was held. This amazing week-long series of discussions on really what the world is made of, on the nature of matter and the new quantum theory. And these steps are the very steps on which this famous group photograph was taken. It's a collection of some of the most brilliant people in the world. Here in the front row, we see Albert Einstein and the great Marie Curie and Max Planck. In the back row standing, the dapper Erwin Schrödinger, and these sort of brash 20-year-olds or mid-20s, Werner Heisenberg and Wolfgang Pauli.
These scientists were the pioneers of quantum mechanics.
I had a huge version of this photograph up on the wall as a poster in my college dorm room. My roommates had their favorite bands, and I had the 1927 Solvay conference, which says a lot.
This was one of the greatest meetings of minds in history. More than half were or would become Nobel Prize winners. Their experiments were showing that deep inside matter, tiny particles like atoms and their orbiting electrons were not solid little spheres. They seemed fuzzy and undefined.
So this group here, these were the folks who had just been plumbing deeper and deeper and deeper to find what they hoped would be a bedrock of what the world is made of. And to their surprise, they found things less and less solid as they dug in. This world was not tiny little bricks that got smaller and smaller. At some point, the bricks gave way to this mush. And what looked like solidity, solidness, in fact, became very confusing and kind of a whole new way of thinking about nature.
The theory of quantum mechanics presented at the meeting was strange. It said that a particle, like an electron, isn't physically real until it's observed, measured by an instrument that can detect it. Before it's detected, instead of being a solid particle, an electron is just a fuzzy wave, a wave of probability.
These objects, like electrons and atoms, when we describe mathematically their behavior, the only thing we can describe is the probability of being at one place or another.
It's like a wave of all those different possibilities. It's not that the electron is in one place or the other, we just don't know. It's that the electron really is a combination of every possible place it could be until we look at it.
Quantum mechanics only tells us the probability of a particle's properties, like location.
Laws of nature were no longer definite statements about what's going to happen next. They were just statements about probabilities. And Einstein felt, well, that's defeat. You're giving up on the heart of what physics has been, namely to give a complete description of reality.
For Einstein, the idea that particles only pop into existence when they're observed is akin to magic. It's said he asked, "Do you really believe the moon is not there when you are not looking at it?" Outside of the formal setting of the conference, he challenged the most vocal supporter of these ideas, the great Danish physicist Niels Bohr.
Einstein would show up to breakfast at the hotel, and Niels Bohr would be there, and Einstein would present his latest challenge. Niels Bohr would sort of mumble and wonder and confer with his younger colleagues. They'd head off to the formal meeting at the Institute, and somehow every night by supper time, Bohr would have an answer. One of the observers said that Einstein was like a jack-in-the-box. Every day he'd pop up with a new challenge, and Bohr would flip this way and that, and then by supper have crushed that one, and it would start all over again.
To Bohr and his colleagues, quantum mechanics not only explained experimental results, its mathematics were elegant and beautiful. And since Einstein hadn't found flaws in their equations, they left the Solvay meeting feeling more confident than ever in their ideas. But Einstein didn't give up his conviction that quantum mechanics was flawed. And in his refusal to accept the weird implications of the theory, he would wind up uncovering something even weirder. In 1933, with the Nazi Party in power in Germany, Einstein chose to settle in America and took a position at the Institute for Advanced Study in Princeton, New Jersey. He recruited two physicists to help him, Nathan Rosen and Boris Podolsky. And in 1935, at afternoon tea, the three men spotted a possible flaw in quantum mechanics that would shake the very foundations of the theory. They noticed that the mathematics of quantum mechanics led to a seemingly impossible situation. Today, Robert Dijkgraaf is the director of the Institute.
Apparently Podolsky said, well, Professor Einstein, this is very important in your arguments showing that quantum theory is incomplete. So they got this very animated discussion, and what kind of happens still is now you have a bunch of scientists discussing, and at some point someone says, let's write a paper together. So they did.
Their paper, known today as EPR, argued that the equations of quantum mechanics predicted an impossible connection between particles, a seemingly magical effect. It would be like having two particles, each hidden under a cup. Looking at one mysteriously causes the other to reveal itself too, with matching properties. Quantum theory suggested this effect could happen in the real world. For example, with particles of light, photons. The equations implied that a source of photons could create pairs in such a way that when we measure one, causing it to snap out of its fuzzy state, the other mysteriously snaps out of its fuzzy state at the same instant, with correlated properties. The 1935 paper that described this effect has become Einstein's most referenced work of all. It has captivated generations of physicists, including Anton Zeilinger.
The Einstein-Podolsky-Rosen paper fascinated me, and I had to read it at least 5 or 6 times until I finally understood what goes on. And then it didn't let me go again.
Another way to think of the paired particles is to imagine a game of chance that's somehow rigged.
Suppose I had a pair of quantum dice. I put these 2 quantum dice in my little cup, throw them. I look at them, they show the same number, 6. I put them again in the cup, throw them again. Now they both show 3. I put them in again, throw again. Now they both show 1. Point now being, what I see here is, I see 2 random processes, namely each die showing some number, but these 2 random processes do the same. was really mind-boggling.
How could two particles act in unison even when they're separated from each other?
Central to the EPR argument is that these particles can be separated at an arbitrary distance. One could be here at Princeton, one could be in the Andromeda galaxy. And yet, according to quantum mechanics, a choice to measure something here is somehow instantaneously affecting what could be said about this other particle. You can't go from Princeton to Andromeda instantly. And yet that, they argued, is what the equations of quantum mechanics seem to imply. And that, they said, so much the worse for quantum mechanics. The world simply can't operate that way.
For Einstein, this strange effect conflicted with the most basic concept we use to describe reality: space. For him, objects, particles, everything that exists is located in space. Space, together with time, was the key ingredient in his theory of special relativity, with its famous equation E equals mc squared.
Einstein, of course, was the master of space-time. He thought that if something happened here, that shouldn't immediately and instantaneously change something that is going on over there, the principle of locality, as we currently call it.
For Einstein, it's simply common sense that if objects are separated in space, for one to affect the other, something must travel between them. And that traveling takes time. Quantum particles acting in unison could be explained if they were communicating. One particle instantly sending a signal to the other, telling it what properties it should have. But that would require a signal traveling faster than the speed of light, something Einstein's theory of special relativity had proven impossible. And it would mean the particles were fuzzy and undefined, until the moment they were observed. Instead, Einstein thought the particles should be real all along. They must carry with them a hidden layer of deeper physics that determines their properties from the start. Almost the way that magic tricks, while appearing mysterious, have a hidden explanation. But this hidden physics was missing from quantum theory. So Einstein, Podolsky, and Rosen argued that quantum mechanics was incomplete.
Podolsky was very enthusiastic about this project. In fact, he was so enthusiastic that he ran to the New York Times and told them the news. So Einstein was really upset with Podolsky, and apparently he didn't speak to him anymore.
When Niels Bohr heard of Einstein's paper, he wrote an obscure response, arguing that one particle could somehow mysteriously influence the other. This seemingly impossible phenomenon became known as quantum entanglement. But Einstein dismissed it as spooky actions at a distance. No one could think of an experiment to test whether Einstein or Bohr was correct. But that didn't stop physicists and engineers from making use of quantum mechanics to do new things.
In the 30s and 40s, the debate around the EPR paper sort of dies down, but quantum theory actually takes off. The mathematics leads to all kinds of amazing developments.
Entanglement aside, the equations of quantum mechanics enabled the scientists of the Manhattan Project to develop the atomic bomb. And in the years after the Second World War, researchers at Bell Labs in New Jersey used quantum theory to develop one of the first lasers.
In our laboratories, men experiment with a light once undreamed of in the natural world.
And build small devices that could control the flow of electricity, transistors.
It's destined to play a vital role in your future, your electronic future.
transistors became the building blocks of the burgeoning field of electronics. Computers, disk drives, the entire digital revolution soon followed, all made possible by the equations of quantum theory. Yet Einstein's questions about entanglement and what it implied about the incompleteness of quantum mechanics remained unanswered until the 1960s, when a physicist from Northern Ireland made a remarkable breakthrough: John Bell.
Bell was a very talented young physics student, but he quickly grew dissatisfied with what he considered almost a kind of dishonesty among his teachers.
Bell insisted that Einstein's questions about quantum mechanics had not been addressed.
He got into shouting matches with his professors. Don't tell us that Bohr solved all the problems. This really deserves further thought.
Quantum mechanics has been fantastically successful, so it is a very intriguing situation that at the foundation of all that impressive success, there are these great doubts.
It's a very strange thing that ever since the 1930s, the idea of sitting and thinking hard about the foundations of quantum mechanics has been disreputable among professional physicists. When people tried to do that, they were kicked out of physics departments. And so for someone like Bell, he needed to have a day job doing ordinary particle physics. But at night, hidden away, he could do work on the foundations of quantum mechanics.
Bell became a leading particle physicist at CERN in Geneva, but he continued to explore the debate between Einstein and Bohr. And in 1964, he published an astonishing paper. Bell proved that Bohr's and Einstein's ideas made different predictions. If you could randomly perform one of two possible measurements on each particle and check how often the results lined up, the answer would reveal whether we lived in Einstein's world, a world that followed common sense laws, or Bohr's, a world that was deeply strange and allowed spooky quantum connections.
We now know with hindsight this was one of the most significant articles in the history of physics, not just the history of 20th century physics, in the history of the field as a whole. But Bell's article appears in this, sort of out-of-the-way journal. In fact, the journal itself folds a few years later. This is not central to the physics community. It's sort of dutifully filed on library shelves and then forgotten. It literally collects dust on the shelf.
A few years later, completely by chance, a brilliant experimental physicist stumbled upon Bell's article.
I thought this is one of the most amazing papers I had ever read in my whole life. And I kept wondering, well, gee, this is wonderful, but where's the experimental evidence?
John worked on Bell's theory with fellow physicist Abner Shimoni, and at the University of California, Berkeley, started work on an experiment to test it. He had a talent for tinkering in the lab and building the parts he needed.
I used to rummage around here and scavenge and dumpster dive for old equipment.
He knew where to find hidden storage rooms like this, which he could raid to salvage spare parts for his experiments.
And this was a power supply for diode lasers. That looks like something I built. Here's a picture of the experiment I did. I had more hair in those days. Here's another picture. This is Stu Friedman, worked on it with me.
Piece by piece, John Clauser and Stuart Friedman constructed the world's first Bell test experiment. They focused a laser onto calcium atoms, causing them to emit pairs of photons that the equations of quantum theory suggested should be entangled. They recorded whether or not the photons passed through filters on each side and checked how often the answers agreed. After hundreds of thousands of measurements, if the pairs were more correlated than Einstein's physics predicted, they must be spookily entangled.
We saw the stronger correlation. characteristic of quantum mechanics. We measured it, and that's what we got.
The outcome was exactly what Bohr's quantum mechanics predicted. The experiment appeared to show that the spooky connections of quantum entanglement did exist in the natural world. Could it be that the great Albert Einstein was wrong? Remarkably, the first people to react to this extraordinary result were not the world's leading physicists.
Ronald Reagan's definition of a hippie was someone who dresses like Tarzan, has hair like Jane, and smells like cheetah.
A small group of free-thinking physicists at the heart of San Francisco's New Age scene got in touch with John.
They call themselves the Fundamental Physics Group. They spelled physics with an F. Some members would experiment with psychedelic drugs. I mean, they were kind of in the flow of the kind of hippie scene. And that group was just mesmerized by the question of entanglement.
The idea was just to discuss fringe subjects with an open mind, and I thought, sure, that's kind of what I do. They were doing their best to link Eastern mysticism with quantum entanglement. They sold a lot of popular textbooks. There were a lot of followers.
Their books became bestsellers, like The Tao of Physics, which highlighted that Eastern philosophy and quantum entanglement both described a deep connectedness of things in the universe.
It was the great cosmic oneness.
The group held meetings at the iconic Esalen Institute.
It was a marvelous, beautiful place where they would discuss all of these ideas. It was right on the Pacific coast with the overflow from the hot tubs cascading down the cliffs into the Pacific Ocean. To my knowledge, no useful connections to Eastern mysticism were ever discovered by the group. But it was fun.
The Fundamental Physics Group may not have uncovered the secrets of cosmic oneness, but in seeing entanglement as central to physics, they were decades ahead of their time. "40 years later, cutting-edge labs around the world are now racing to harness quantum entanglement to create revolutionary new technologies, like quantum computers.
In our everyday computers, the fundamental unit of computing is a bit, a binary digit, 0 or 1. And inside the computer, there's all these transistors which are turning on and off currents. On is 1, off is 0. And these combinations lead to universal computing. With a quantum computer, you start with a fundamental unit that's not a bit, but a quantum bit, which is not really a 0 or a 1, but it can be fluid.
A quantum bit makes use of the fuzziness of the quantum world. A qubit, as it's known, can be 0 or 1, or a combination of both. A particle or tiny quantum system can be made into a qubit. And today, it's not just pairs of particles that can be entangled. Groups of qubits can be linked with entanglement to create a quantum computer. The more qubits, the greater the processing power. At Google's quantum computing laboratory in Santa Barbara, the team has recently succeeded in creating a tiny chip that holds an array of 72 qubits. The task for researcher Marissa Giostina and her colleagues is to send signals to these microscopic qubits to control and entangle them.
Mounted on the underside of this plate, we have the quantum processing chip itself. In essence, a quantum playground, you could say. Each qubit is a quantum object that we should be able to control at will. Thinking about it as the faster version of that PC over there would be a great slight to this. It can be much more than that.
By using entangled qubits, quantum computers could tackle real-world problems that traditional computers simply can't cope with. For example, a salesman has to travel to several cities and wants to find the shortest route. Sounds easy. But with just 30 cities, there are so many possible routes that it would take an ordinary computer, even a powerful one, hundreds of years to try each one and find the shortest. But with a handful of entangled qubits, a quantum computer could resolve the optimal path in a fraction of the number of steps. There's another reason teams like Marissa's are racing to create a powerful quantum computer: cracking secret codes. In today's world, everything from online shopping to covert military communications is protected from hackers using secure digital codes, a process called encryption. But what if hackers could get hold of quantum computers?
A quantum computer could crack our best encryption protocols in minutes, whereas a regular computer or even a supercomputing network today couldn't do it, given months of time.
But while quantum entanglement may be a threat to traditional encryption, it also offers an even more secure alternative: a communication system that the very laws of physics protect from secret hacking. Researchers in China are leading the way. Here in Shanghai, at the University of Science and Technology, Jianwei Pan runs a leading quantum research center. His teams are working to harness the properties of the quantum world. They can send secret messages using a stream of photons in a system that instantly detects any attempt to eavesdrop. Jianwei's team has created a network of optical fibers more than 1,000 miles long that can carry secure information from Beijing to Shanghai. It is used by banks and data companies. But there's a limit to how far quantum signals can be sent through optical fibers. To send signals further, Jianwei's team launched the world's first quantum communication satellite. Above Earth's atmosphere, there are fewer obstacles, and quantum particles can travel much further. Each night, teams on the ground prepare to track the satellite across the sky. Laser guidance equipment locks on and allows signals to be sent and received. The team aims to use this equipment to create a new, secure communication system using quantum entanglement. The satellite sends entangled photons to two users. An eavesdropper could intercept one of the entangled photons, measure it, and send on a replacement photon. But it wouldn't be an entangled photon. Its properties wouldn't match. It would be clear an eavesdropper was on the line. In theory, in this cosmic bell test, the source of the entangled particles is about 1/3 of a mile from each of the detectors. The team must send perfectly timed pairs of photons through the air to each side. At the same time, the telescopes will collect light from two extremely far-off, extremely bright galaxies called quasars. These are among the brightest objects in the sky, emitting light in powerful jets. Random variations in this light will control which filters are used to measure the photon pairs. And since the quasars are so far away, the light has been traveling for billions of years to reach Earth. It makes it incredibly unlikely that anything could be influencing the random nature of the test. If the experiment is successful, the team will have tackled the loophole and shown that quantum entanglement is as spooky as Bohr always claimed. Dominic and Jason are at one telescope.
Hello, Anton.
Anton is at the other.
Wir hatten gerade schon den Quasar im Field of View oder in der Iris.
Mit der Quelle funktioniert es auch.
Ja, Quelle funktioniert, der Kontrast ist super. Läuft.
Das Licht jetzt.
Okay.
Ciao.
Ciao.
With clear skies finally overhead, the huge telescopes awaken. Poised to collect light from distant quasars.
Moving.
Dominic, this is Darkon level, is the Spiegelbrenner.
Arrived.
Darkon level.
Okay, this is good.
So we're doing everything at once now. So the guys for the links are setting the state of the entangled photon pair. We try to acquire the quasar. We're just centering it and making the field of view as small as possible to be sure that we only have the quasar.
Okay.
It's guiding now?
Yes, let's wait one more image.
Okay.
Of this one.
All right.
Great.
Yes.
Okay.
Yeah, that's good.
Looks like 90, let's say 91 to be conservative, for purity.
With the telescopes now locked on to two different quasars, the team begins to take readings.
Red counts 12,000, blue counts 7,000.
We do the full cosmic bell test.
What?
Yeah, we're doing a full cosmic bell test.
It's working. Light from the quasars is selecting which filters are used to measure the entangled photons.
It is exciting. It is. Now we do have a test, but it's not clear what the outcome will be.
Two months later, back in Vienna, the team analyzes the experimental data.
This might take a second. The numbers look really great, and it is extremely pleasing to see that all this works so nice. We clearly see correlations that correspond to quantum mechanics.
The results show entanglement. And since the light from the quasars controlling the test was nearly 8 billion years old, it's extremely unlikely that anything could have affected its random nature. This remaining loophole seems to be closed.
The experiment we did is just fantastic. The big cosmos comes down to control a small quantum experiment. That in itself is beautiful.
You know, honestly, I still get chills. I mean, when I realized what our team was able to do in this intellectual journey that stretches back to the early years of the 20th century, there's hardly any room left for a kind of alternative Einstein-like explanation. We haven't ruled it out, but we've shoved it into such a tiny corner of the cosmos as to make it even more implausible for anything other than entanglement to explain our results.
Accepting that entanglement is a part of the natural world around us has profound implications. It means we must accept that an action in one place can have an instant effect anywhere in the universe, as if there's no space between them. Or that particles only take on physical properties when we observe them. Or we must accept both.
We're left with conclusions about the universe that make no sense whatsoever. science is stepping outside of all of our boundaries of common sense. It's almost like being in Alice in Wonderland, right, where everything is possible.
It was first seen as an unwelcome but unavoidable consequence of quantum mechanics. Now, after nearly a century of disputes and discoveries, spooky action at a distance is finally at the heart of modern physics. At the Institute for Advanced Study, where the concept of entanglement was first described, researchers are now using it in their search for a single unified theory of the universe, the holy grail of physics. Einstein's theories of special and general relativity perfectly describe space, time, and gravity at the largest scales of the universe, while quantum mechanics perfectly describes the tiniest scales. Yet these two theories have never been brought together.
So far, we've not yet had a single complete theory that is both quantum mechanical and reproduces the prediction of Einstein's wonderful theory of general relativity. Maybe the secret is entanglement.
What if space itself is actually created by the tiny quantum world? Just like temperature, warm and cold consists simply of the movement of atoms inside an object. Perhaps space, as we know it, emerges from networks of entangled quantum particles. It's a mind-blowing idea.
What we are learning these days is that we might have to give up that what Einstein holds sacred, namely space and time. So he was always thinking, well, we have little pieces of space and time, and out of this we build the whole universe.
In a radical theory, known as the holographic universe, space and time are created by entangled quantum particles on a sphere that's infinitely far away.
What's happening in space, in some sense, all described in terms of a screen outside here. The ultimate description of reality resides on this screen. Think of it as kind of quantum bits living on that screen. And this, like a movie projector, creates an illusion of the three-dimensional reality that I'm now experiencing.
It may be impossible to intuitively understand this wild mathematical idea, but it suggests that entanglement could be what forms the true fabric of the universe.
The most puzzling element of entanglement, that somehow 2 points in space can communicate, becomes less of a problem because space itself has disappeared. In the end, we just have this quantum mechanical world. There is no space anymore. And so in some sense, the paradoxes of entanglement, the EPR paradox, disappears into thin air.
Truly understanding quantum mechanics will only happen when we put ourselves on the entanglement side, when we stop privileging the world that we see and start thinking about the world as it actually is.
Science has made enormous progress for centuries by sort of breaking complicated systems down into parts. When we come to phenomena like quantum entanglement, that scheme breaks. When it comes to the bedrock of quantum mechanics, the whole is more than the sum of its parts.
The basic motivation is just to learn how nature works. What's really going on? Einstein said it very nicely. He's not interested in this detailed question or that detailed question.
To the broiling heat of Earth's closest neighbor, radical weather is the norm in the solar system. We do have our own extremes here on Earth, but they pale in comparison to the fastest, dustiest, wettest, and most brutal alien storms. On Earth, the sun drives our weather. and sometimes drives it wild. When hot and cold collide in the atmosphere, watch out. This is true locally and globally. But storms on other planets are bigger, badder, and stranger than their counterparts on Earth. Why is that? Because of the sun? If not, what else fuels their fury? The basic laws of nature, the rules of the game, are pretty much the same wherever you go in the solar system. But every planet has its own way of playing the game. Right now on Mars, the entire planet is being covered in dust. This global dust storm blocks 99% of the sun's rays from reaching the planet's surface. It's actually a system of smaller but still massive storms churning dust high into the atmosphere. Once it starts, it takes months for Martian skies to clear.
Mars is just the most dramatic weather in the solar system in some senses. It's very rare in the solar system you get a weather event that can take out the whole planet.
So if the basic rules of hot and cold are the same on Mars, why is the weather so different from Earth? For one thing, Mars is half the size of Earth. It's also 50% further from the sun, so it's much colder. The average temperature on Mars is minus 80 degrees. That's almost 130 degrees colder than Earth. And the atmosphere is extremely thin and composed mostly of carbon dioxide. But perhaps the most important difference is this: Mars is a global desert.
What would Earth be like without water? Well, it'd probably have a lot of dust.
There's no liquid water at the surface of Mars, and there's very little water in the atmosphere, and so there's nothing to sort of keep the dust down.
On Earth, dust storms are localized and short-lived.
The reason for that difference in scale is that the storms are generating their own weather on Mars, whereas on the Earth, they're slave to the weather that's going on around them.
In other words, on Earth, the global weather system creates dust storms. On Mars, the storms create a global weather system. Astronomers have always been able to see big Martian dust storms easily with Earth-based telescopes. But what they couldn't see was what caused them. That would require a trip to Mars itself. In 2003, NASA landed 2 rovers called Spirit and Opportunity on the Martian surface. Their mission? To learn more about the geology of the red planet. NASA engineers always assumed that as these 2 vehicles roamed the Martian surface, dust would build up on their solar panels.
If you have a lot of dust that's falling down out of the atmosphere and coating the panels, pretty soon you're not getting much sun to the silicon. And in fact, we thought that was what was going to kill the rover Spirit and Opportunity.
Only it never happened. The rovers didn't die as expected. As dust built up on the panels, somehow something would clean them off. But how could this be? NASA engineers were baffled until the rovers themselves saw the culprit. Martian dust devils.
It turns out that dust devils were sort of our white knight. They came along and cleaned off the solar panels just at the time we were expecting to start having some problems.
There are beautiful photos that actually show dust devils moving across the Martian atmosphere, and ghostly soldiers moving out there in the distance.
A dust devil is really an extreme form of rising hot air or convection.
And that hot air wants to go up, and it comes up just like, water going down a drain. Well, this is air that just spirals up into the colder parts of the atmosphere.
Whenever warmer air, which is less dense, rises up through cooler air, which is more dense, it rotates as it swirls upwards. Convection can be very powerful, strong enough to lift things up. On Earth, it lifts moisture, and that's how thunderstorms form. But on Mars, there is no moisture, so it lifts dry, dark dust and creates giant dust storms instead. Once airborne, Martian dust clouds absorb sunlight and heat the atmosphere. This supercharges the convection, lifting still more dust.
That produces more winds, which bring up more dust, and these things can spread up to thousands of miles across, or even, in some cases, they can envelop the entire planet.
And because the Martian atmosphere is so thin, it doesn't take much to get this cycle going.
You get a lot more difference between the surface temperature and the air temperature, and so the convection on Mars is very much more vigorous.
As a rule, Earth doesn't get the temperature extremes that Mars does. But sometimes, here and there in the deserts of Earth, convection can be very Martian-like. And we get dust devils, too. But at Arizona State University, Lynn Necrace makes dust devils to order in a lab to study them up close. He uses a vortex generator and substitutes lighter, dry ice for dust. What he creates is not an exact replica of how real dust devils form, but good enough to see how they pick up dust and debris.
Natural dust devils usually form from the bottom up, as opposed to tornadoes, which form from top down. So what happens when we turn this on, we have the airflow starting, and as the airflow starts to rotate from the fans down to the floor, we actually end up having the vortex form.
In other words, the vortex generator, basically a huge vacuum cleaner, imitates the swirling action of convection.
You can see here there's a wider base where larger particles of the dry ice are being swept up and gets wrapped up and tightens as it expands upward. The center of the core is where the majority of the lifting would occur.
Martian dust devils have been helpful, keeping the rovers clean. But could they actually be making a mess of the rest of the planet? Some scientists think there are so many at any one time, and they lift so much dust into the atmosphere, that together they trigger these much larger dust storms.
It starts wind patterns, and the air's warmer over here, and it's colder over here, and the air starts moving around. Pretty soon you're spreading dust over the whole planet.
And we found measurements that indicate there's up to maybe 200 dust devils per square mile per day during some parts of the summer.
And they can range from a couple of 100 feet tall to devils that stretch 6 or 7 miles high.
You can get just towering monsters of dust devils that we would never see on the Earth. The kind of maximum-sized dust devils you see on Mars are more like tornadoes on the Earth, where they're going up almost 10 kilometers. So these things are just real monster systems.
Back at Arizona State University, scientists blow crushed walnut shells as silicate particles in the Planetary Geology Wind Tunnel to replicate dust and wind conditions on Mars.
If we can understand and sort of replicate what's going on, then we can, in a sense, understand how the Martian surface has been changing and continues to change as time goes on.
Oddly enough, their studies reveal that it's easier for winds to loft larger sand particles into the air than smaller dust particles.
This is because there's cohesional forces and static forces between the very small, fine dust grains. We imaged the rover deck and actually found that sand seemed to have bounced onto the solar panels, and we can see the skip marks across the surface. And this is interesting because we don't usually see sand typically reach that high.
Dust devils on Earth never have the punch to produce that kind of chaos here. Lucky for us. But what would happen to Earth if a giant Martian-style dust storm did overtake us?
If you had dust storms of Martian size on the Earth, you would find your city being enveloped in an orange-tan haze.
Air quality plunges as the storm churns. Dust blots out the sun, shutting down photosynthesis. No plants, no food. Temperatures would plummet. 65 million years ago, an asteroid may have struck the Earth, creating these same conditions, wiping out the dinosaurs.
It's not going to happen on the Earth, though, because there's going to be rainfall and moisture condensing on the dust grains and so forth and dropping them out of the atmosphere. So it's very hard for something like that to spread in the climate conditions that we have on Earth.
Forecasting Martian weather may someday be just as important as forecasting the weather on Earth. If we ever want to send a manned mission there,
The word environment no longer really applies just to the meadow next door and the little stream down at the end of town. It's the whole inner solar system. I mean, that's really our environment now.
the sun's energy bathes all the planets. On Earth, it creates hurricanes. On Mars, planet-wide dust storms. But with almost no solar energy, distant Neptune produces violent and powerful winds. Where do they come from? And just how bad are they? If Neptune's winds were to travel to Earth, these alien storms would literally blow us away. The orbit of Neptune lies 3 billion miles from the Sun, at the outer edge of the solar system. There's a lot we don't know about this big blue planet. Neptune's jet stream winds blast as fast as 1,500 miles an hour in its upper atmosphere. But how? The sun controls the weather on Earth and Mars, but it barely reaches out here. No sunlight means freezing temperatures, an average of minus 392 degrees Fahrenheit. So if there's no sun and no heat, where do these incredible winds come from?
One of the interesting puzzles is that as you go further out in the solar system, you get further from the sun, the winds don't go down. You still get very strong winds.
The energy for Neptune's winds must come from somewhere, and scientists are working to figure it out.
Neptune's energy is certainly not going to be powered by solar radiation. In fact, the energy we detect coming out from the planet in the infrared as heat is 2.5 times the energy coming in from the sun.
So the planet is creating its own heat, not from its core, which is made of rock and ice, but wrapped around this icy center is a mantle of ammonia, methane, and water, all being squeezed by enormous pressure and generating tons of heat. So while Neptune is frigid on the outside, on the inside it's giving off a lot of heat. This heat may help generate Neptune's winds, but they're still too strong to come from the mantle alone. Something else is pushing them faster and faster. Earth has a hot core too, and it's a lot closer to the sun. So why don't we have winds like Neptune? For one thing, our oceans store and release energy, and that helps generate our weather.
It adds energy in places, takes it out in others, in a very complicated system.
This complicated system produces a lot of wind. And just where are Earth's fastest winds found? Surprisingly, not over the ocean. They blow instead over the top of a fairly modestly sized mountain. New Hampshire's Mount Washington.
The highest winds ever observed by human beings were right here on Mount Washington at 231 miles an hour on April 12th in 1934.
Mount Washington Observatory, a private, non-profit scientific institution, is responsible for tracking the weather and climate atop the 6,288-foot-tall mountain. This remote weather station, accessible only by snow tractor in the winter, has kept daily records for the last 76 years.
It's definitely one of the most extreme locations on the planet. We regularly see in the wintertime winds exceeding 100 miles per hour every few days.
Nowhere near as ferocious as Neptune, yet still pretty strong. But why does this mountain, 1/5 the size of Everest, produce such fierce gusts?
We're at a place where we have winds converging from various directions, coming from the Ohio River Valley, coming down from the St. Lawrence River Valley, coming up the eastern seaboard, all converging here in this area on top of Mount Washington.
The elevation change from the valley floor to the summit of Mount Washington is very significant for any mountain range. It's over 4,000 feet, so air is forced to go over the mountaintop and forced to squeeze in there, and is accelerated as it's squeezed over the mountaintop.
And they measure it every hour, on the hour, 24 hours a day, 7 days a week.
It's blowing over 100 out here right now. Ice is forming on the instruments more quickly. It's time to go up and de-ice the instruments, even though it's blowing over 100. We gotta do it every hour now.
Ironically, Earth's uneven surface, which channels winds into powerful gusts on Mount Washington, ultimately knocks them down over time. And this is the big difference between weather on Earth and weather on Neptune. Earth has mountains that slow winds down. Neptune is as smooth as a cue ball.
It's not so much a question of you're driving them stronger, because you're not. It's just that there's nothing to slow them down.
Simply put, once Neptune's winds get blowing, there's nothing to get in their way. So what would an average Neptune wind speed of 850 miles an hour do to us here on Earth?
We have parking level winds in the Earth sometimes above 100 miles an hour. We consider that pretty dangerous. So if we sat with 900-mile-an-hour winds from Neptune on the Earth, we would probably start wiping out everything on the surface and scraping everything off.
Giant Neptune takes wind and transforms it into something extreme and almost unrecognizable. But orbiting just beyond the rings of Saturn is a small moon that does the same thing to rain. This is Titan, where an everyday rain shower would turn Earth into an explosive fireball. It's a cloudy day, and a gentle rainstorm starts. Here on Earth, you'd grab your umbrella and consider it a minor inconvenience. But this isn't Earth, and it's no ordinary rain. You're on Titan, a small moon of Saturn. And in this chemical downpour, you'd need more than an umbrella to protect you. The rules of Earth weather definitely don't apply here. But Earth and Titan are alike in a lot of ways. On Earth, we have a solid surface, a protective atmosphere, and plenty of water. All these things make life on our planet possible. There's really nowhere else quite like Earth anywhere in the solar system. But Titan comes close. Like Earth, it has a solid surface. And that's not all.
Titan has an atmosphere that's, in general, very similar to Earth's. In some ways, it's mainly nitrogen like Earth's atmosphere. It's rich with organic material, also like Earth's atmosphere.
But similar isn't the same. Here on Earth, our atmosphere has a huge supply of water in it all the time, constantly evaporating and raining back down, like here on the Hawaiian island of Kauai.
Today we're on the slopes of Mount Waialeale, which is the cloud-shrouded mountain behind us. It rains over 40 feet a year here.
Earth's water cycle starts when warm, moist ocean air rises, forming clouds that eventually condense into rain. The rain falls back onto the land, where it eventually drains back into the ocean, starting the cycle again.
When water evaporates, it absorbs solar radiation. When water condenses, it releases all that energy into the atmosphere. And this transfer of heat helps to moderate conditions on Earth.
Earth's water stores as much as 80% of the sun's heat, helping keep our temperatures steady from the equator to the poles. Scientists theorize that Titan might have water or some other liquid that might produce a similar effect. And in 2004, when NASA's Cassini probe visited Saturn, it found some pretty good evidence to support that idea.
If you went to Titan and you were looking at the landscape, you would see something that in some ways would look almost familiar to you. You might see big mountains and valleys that were carved out by running liquids.
In fact, as Cassini flew past hazy Titan, its radar read the surface below. Scientists saw channels cutting across the surface, much like rivers on Earth do. Some as long as 900 miles. The first strong evidence of liquid on Titan.
There are large bodies of liquid on the surface of Titan. Nowhere else in the solar system except for the Earth are there any large bodies of liquid.
Could water, the liquid that carves Earth's mountains and valleys, also be carving these features on Titan's surface? Or could it be something else? The problem is that Titan is too far away from the sun. If it was water, it would be frozen solid.
It's about minus 300 Fahrenheit on Titan, so things behave very differently on Titan than on Earth. Because it's so cold, methane, which is a gas on Earth, is a liquid on Titan.
One mystery solved. But just because methane is a liquid on Titan's surface doesn't mean it's part of a weather cycle like water on Earth. So how do we know that this methane also falls from Titan's sky? That answer is shrouded in mystery, literally.
Titan is completely covered in a thick haze of smog particles, like a very, very bad day in Los Angeles.
Despite the haze, the Cassini probe once again revealed the answer.
We can see the upper clouds, and we can see evidence for rainfall because the clouds drop very precipitously. We hypothesize that we're seeing the effects of rainfall.
Methane rainfall.
We think that Titan has methane monsoons, so we think that sometimes Titan has a lot of rain that is able to carve rivers and leave large fluvial deposits on the surface.
Cassini's radar imaging also revealed large methane seas on Titan's surface.
If you have liquid methane on the surface, in a lake for example, that methane can evaporate off and become methane gas in the atmosphere. So you have kind of a cycling of methane between liquid phase and gaseous phase and between the surface and the atmosphere that's very similar to the water cycle that occurs on the Earth.
But methane is a flammable gas. So why isn't Titan on fire?
For any combustion, you need two things. You need both a fuel, which methane is, but you also need oxygen. And on Titan, you lack the oxygen. So the whole thing is basically a big fuel canister, but there's no oxygen with which to burn it, and so it's all very stable.
If it were cold enough here on Earth to produce methane rain, the oxygen in our atmosphere would create a worldwide firestorm. Luckily for us, that can't happen. Titan's methane cycle makes it both alien and familiar to us.
To me, Titan is very exciting because all the materials are so different, and yet these processes produce very similar landscapes to what we see on Earth.
Titan proves that where alien weather is concerned, looks can be deceiving. On Jupiter, it's all about size. Drop the great red spot onto our world, and it makes even our worst hurricanes look like a breeze. This is the biggest and oldest storm in the solar system, and Jupiter's most famous feature. It even has its own name, the Great Red Spot.
It's about 2 or 3 times the size of the Earth, which makes it the mother of all storms.
We've known about the Great Red Spot in Jupiter's southern hemisphere for more than 300 years.
When Galileo invented the telescope, within a few tens of years, people had seen the Great Red Spot, and it's still there.
Familiar yet mysterious. Nobody knows how the Great Red Spot formed. But scientists are finally probing below Jupiter's cloud tops to uncover more about this enormous alien storm. The storm is powerful. With wind speeds of 300 miles per hour, it rises miles above the surrounding clouds. On Earth, we have storms that seem similar, though smaller and milder. Hurricanes, also known as cyclones or typhoons, depending on where they form. They're our most destructive weather systems. But is there more than just a passing resemblance between Earth's cyclones and Jupiter's red spot?
When you look at the Earth from space at a hurricane, it's this big swirling pattern. It's round, it rotates. Jupiter's big storms look big and round and cloudy, and they rotate. But there the similarity ends.
In a hurricane, there is an internal core, which is called the eye of the tropical cyclone, and that's a region of very calm winds and no clouds, and usually has a size of about 10-20 kilometers in diameter. And then away from the eye, there is the eye wall. Those are really cloudy regions with a lot of rain. And as you move outward, there is a whole region of about a couple of 100 kilometers with very, very strong winds and very strong rain.
Hurricanes draw power from heat in our oceans. But Jupiter has no oceans, and the sun isn't close enough to power a storm as big as the Great Red Spot. So where does it get its strength? Part of the answer is Jupiter's size. It's the largest planet in the solar system, almost as big as all the other planets combined. This mass generates a very strong gravitational pull, which in turn creates interior heat that rises to the surface. Another piece of the puzzle may be Jupiter's hypersonic rotation. Despite being much larger than Earth, Jupiter's day lasts only 10 hours. In other words, it spins incredibly fast. Could energy from this dizzying spin feed the Great Red Spot?
The weather is really dominated by this fast spin. There's shearing between different latitudes, and that shearing, plus a lot of heat that comes up from the interior of this very massive object, 290 times the mass of the Earth, leads to very violent storms.
Both Jupiter's and Earth's storms spin around in a familiar spiral shape. On Earth, it's because of an effect called the Coriolis force.
I'm sitting at the North Pole, and I want to throw a ball down to a friend who's in Los Angeles. And so if I threw the ball in that direction, the Earth rotates, and the ball will end up in the middle of the Pacific rather than in Los Angeles. So it's like if the trajectory was deflected to its right. And that's what we call the Coriolis force.
This force spins storms clockwise in our southern hemisphere. But there is a stark difference between Earth and Jupiter. The Great Red Spot is in Jupiter's southern hemisphere, and yet it spins counterclockwise. This is because of some other powerful winds.
It's bounded by jets, which are moving in opposite directions. And so like a cog between two conveyor belts, they're just feeding energy and momentum into the system.
Jupiter's complex jet streams spin the storm into organized chaos. But the greatest difference between Jupiter's red spot and our storms may be Earth's solid surface. Once a hurricane hits land, it comes apart pretty fast.
Where they come over land or over mountains, their behavior is very different from where they form over the oceans, and over warm oceans in particular, where we get hurricanes. And on Jupiter, there's obviously no solid surface.
With no land mass to stop it, the Great Red Spot just keeps on spinning and spinning and spinning. Scientists hope to learn more about our weather by continuing to study the storm.
On Earth, there's a limit to how far ahead you can predict the weather. On Jupiter, we can forecast where the red spot is going to be months in advance. It's practical value to understand what makes weather on Earth so unpredictable, and aspects of the weather on Jupiter are much more predictable.
Unpredictable or not, Earth's weather never gets as violent as on Jupiter. That's lucky for us, because if we shrank the Great Red Spot down to fit on Earth, we'd be in for disaster.
On the Earth, we go up to Category 5 hurricanes, let's think about Category 10 hurricane here. Not much would be left.
Alien storms are vastly different everywhere you go in our solar system. Even our next-door neighbor, Venus. They say we're sister planets. Lucky the resemblance doesn't include weather. Otherwise, we'd get seriously burned. Venus may be our nearest neighbor, but somehow its weather is radically different from ours. The second planet from the Sun is a cross between a toxic waste dump and Death Valley, but even worse.
So it's almost a planetary definition of hell.
The temperature is 900 degrees Fahrenheit. The pressure on the surface is the same as half a mile below the Earth's ocean. And if that's not enough, the upper atmosphere of Venus is choked with sulfuric acid clouds and winds clocked at 250 miles an hour.
To get a comparison for Venus, the best thing to do is climb inside of your oven and crank it up. And then in terms of pressure, you're talking about deep sea diving. It's like nothing. There's nothing comparable on the Earth. It's just a very, very extreme object.
On Venus, there's just no escaping the heat.
If you built up a hot spot on Venus, the massive atmosphere would just carry that heat away and spread it around.
But Venus shines so brightly in the night sky because its thick clouds reflect almost all the sunlight it receives. In fact, some early scientists assumed Venus would have moderate Earth-like temperatures.
When we went by Venus in 1962 with a spacecraft, we thought we would find a surface at 90 degrees Fahrenheit, sort of like Miami, Florida.
We were dead wrong. Something else must be at work on Venus. But what? So why doesn't Venus cool off the same way Earth does?
On the Earth, for example, we have sunlight coming in, hitting the surface of the Earth. Earth warms up a little bit, but the oxygen and the nitrogen in the atmosphere don't impede the light, so when it gets released out in the infrared, it goes right through the atmosphere and leaves and goes into space.
But on Venus, the atmosphere is 97% carbon dioxide. giving a whole new meaning to the greenhouse effect.
It becomes very, very hard for the surface to get its energy out.
So Venus really taught us a lesson, that if you have a blanketing gas, a greenhouse gas, it can warm up the atmosphere tremendously.
But why does Venus have so much more CO2 in its atmosphere than Earth? The two have much in common. They're even called sister planets. They're almost the same size, have roughly the same amount of carbon, and billions of years ago, both had lots of water. But eons ago, their paths mysteriously diverged. On Earth, water fostered life.
The Earth has most of its carbon in life forms, in the trees and the animals. But if you took all that carbon that's in the near-surface rocks and burned it up or released it, you would then create an atmosphere very much like Venus.
Venus's close proximity to the sun made it too hot to sustain liquid water. Instead, its water evaporated into the atmosphere, trapping the heat deposited by the sun and creating a runaway greenhouse effect. Once in the atmosphere, the water molecules were exposed to solar ultraviolet rays that broke the molecules apart.
It really wasn't recognized by the scientific community how important the greenhouse effect was prior to going by Venus and seeing this amazing place where it was 900 degrees Fahrenheit, not 90.
It took several doomed missions to Venus to figure it out. Starting in the 1960s, both the United States and the Soviet Union sent unmanned probes past the planet and down to its surface. It didn't take long before Venus crushed and burned them. Then, in 1981, the Soviet lander Venera 13 set a record for survival on the surface of Venus. 2 hours and 7 minutes. It was able to take pictures and samples of the surface before being overcome by the heat.
You're sitting there with this 900 degrees Fahrenheit heat all around you. It's going to get in there and bake you after a while.
Scientists one day hope to send a probe to Venus that can survive its hellish environment, to help us confirm our theory of how this planet went astray. Because if circumstances were just a little different, our sister planet might just be our twin. Remove our atmospheric shield, and you're on the road to hell.
As soon as you're heated up to something like 400 degrees or so, you probably start getting some smoldering smoke, and way before it hit the 900 degrees, the Earth would burst into flames because all the oxygen around.
Once the oceans boiled away, the carbon locked in rocks on the ocean floor would cook, and over millions of years re-enter the atmosphere.
Probably if you came back to the Earth system after this happened, you'd find a planet looking much like Venus.
We're a long ways away from such a drastic change, but it's sobering to look at Earth's sister planet when the sister planet went on a very different track than we did.
So cosmic forces turned Venus into a planetary barbecue. But on this violent, stormy world, time and the elements have produced some of the strongest thunderstorms ever measured. Welcome to Saturn. Lightning cuts the sky. This violent weather system grows bigger than the entire United States as it pummels the atmosphere with the most powerful lightning ever seen. Except this lightning can't be seen, because these bolts are electrifying the skies over Saturn. Despite the raw power of Saturn's lightning, scientists have been unable to see it, partly because Saturn's rings are too bright.
The rings are so bright, if you were on the night side of Saturn, it would be considerably brighter than the Earth under a full moon.
But Saturn also hides its lightning within thick, choking clouds of ammonia.
It's probably 100 kilometers down that the lightning is happening, and that complicates seeing the lightning flashes.
But the lightning is there, and scientists know it because they've heard it. Radio wave detectors on the Cassini orbiter have recorded the sound of Saturn's lightning.
We can hear the static of lightning just as you could with an AM radio going down the highway on Earth.
And this static reveals the power of the lightning that we can't see.
You can measure the energy in those radio waves and compare it with the energy that your radio picks up when there's a thunderstorm around on Earth. And the Saturn ones are big. They're more powerful, maybe 100 times.
And Earth's lightning can help scientists understand how storms work on Saturn. Within Earth's storm clouds, just like in Saturn's, updrafts drive moisture higher, causing ice to form. These ice crystals rub against each other, take on a positive charge, and become attracted to negatively charged water droplets lower in the cloud. This sets the stage for a potentially powerful discharge of energy.
Once you get that charge separation that builds up so intensely that some theorize that it can be as strong as 100 million volts, that the cloud then must release that energy.
On Saturn, the same thing happens on a much larger scale. In fact, the lightning is 100 times stronger than Earth's. That's a staggering 10 billion volts of electricity. Thunderstorms in Saturn's southern hemisphere span thousands of miles and can last as long as a month. But scientists aren't sure what makes Saturn's storms bigger and longer lasting. It could be Saturn's supersaturated atmosphere.
Probably the fact that there's more water in the atmosphere, pound for pound, on Saturn makes the storms bigger.
More water droplets means more friction, which means bigger lightning bolts. But energy emerging from the planet may also contribute to the power in Saturn's thunderstorms.
It turns out that where Lightning Alley is on Saturn is a place where the winds are flowing the slowest. If you go deep down in the atmosphere, you'll see the same winds as you do up high. It's a place where the energy being released deep down below can make it on up to the upper atmosphere without being sheared apart, and allows storm systems to be organized.
Earth's atmosphere isn't built that way. So, as violent as our storms get, they're nothing compared to the systems on Saturn. Even a run-of-the-mill mega thunderstorm on Saturn would devastate us here.
A Saturn-sized thunderstorm on the Earth would mean a thunderstorm that grows to cover all of North America and presumably has very strong winds and rain. This is something that's unprecedented on the Earth.
Saturn's hyper-violent thunderstorms are proof that our planetary neighbors have weather far more ferocious than ours. But the laws of physics that create Saturn's storms are the same laws that create our own weather. Massive dust storms, unrelenting winds, killer lightning, powerful hurricanes, and searing heat.
Some with moons. Their names may be unfamiliar. Eris, Makemake, Haumea, but they hold clues to all our origins. And the first of these worlds, and the one we'll reach in 2015, is the king of the Kuiper Belt, Pluto. The long journey of NASA's New Horizons mission began in 2006 aboard America's biggest, baddest rocket, tricked out with every conceivable booster.
We built a very light spacecraft and bought a very large launch vehicle, and the combination is ferocious.
But in some sense, it all began in 1930 with Clyde Tombaugh, 24 years old and fresh off a farm in Kansas, but willing to spend long hours scanning star fields to find a moving point of light. Humanity's first glimpse of Pluto. The dream of actually getting to Pluto began with a 6-year-old boy in love with science who grew up to lead a team of brilliant researchers and engineers with dogged persistence through decades of planning and building and testing. A race against time just to get to the launch pad.
Exploring the outer solar system, because it's so far, takes a lot of time. It requires a lot of patience, a lot of dedication, a lot of perseverance. But it's the frontier.
Assuming all goes well at Pluto, NASA may choose to extend the adventure further out into the Kuiper Belt, the solar system's mysterious third zone.
This is maybe the one chance in my lifetime that we're going to get a spacecraft out there and look up close at one of these Kuiper Belt objects.
December 6, 2014.
We have an all wake up of the New Horizons spacecraft.
New Horizons wakes up for the last time from hibernation.
New Horizons is speeding towards Pluto at a phenomenal rate, and we can't wait for it to get there.
January 27, 2015, 6 months of approach science begins. July 14, 2015, New Horizons' long journey, 3 billion miles, 9 years in flight, and 85 years of speculation about Pluto climaxes in one day of close approach and flyby.
You know, we're rounding third base and we're headed home.
The dream, the adventure, the promise of discovery. That's what makes 2015 the year of Pluto. Studying Pluto and its neighbors from Earth is one of the toughest challenges in astronomy. It takes the largest telescopes and most advanced instrumentation on the planet. And it's tough even for the Hubble Space Telescope. And it takes time, from the discovery of Pluto in 1930 to NASA approving the New Horizons mission in 2001 to arriving at the planet in 2015. It's been 85 years, and time passing is definitely an actor in our story. But it's the combination of human skill, cutting-edge image processing, and sheer bloody-minded persistence that has resulted in the most important discoveries. And that's a tale as true today as back in 1930, when Pluto was first found by Clyde Tombaugh. In 2011, at the SETI Institute near San Francisco, Mark Showalter used Hubble data to discover 2 new moons around Pluto, although he was actually looking for possible rings. Showalter has found rings associated with small moons around other planets.
And that was kind of the motivation for checking out Pluto. It's got 2 little satellites. Satellites raise clouds of dust. Let's see what might be there.
It's easy to take artistic license to show what Pluto's rings might look like. In reality, it's incredibly hard to see faint objects against the dense background star field and the glare from Pluto and its large moon, Charon.
We came up with this trick where you take the images and then you rotate the camera 90 degrees, you take more images, and if you do that all just right, you can do this thing where all that glare cancels out, and what we're left with is just the rings. We could think of it as a stack of images. Think of it as like a cube looking down. So let's turn it on its side. So now if we start peeling off the layers and looking downward through the stack, things suddenly become much, much cleaner. For example, Hydra and Nix show up very, very cleanly. But the thing that immediately caught my eye was this little dot right there. It's not a perfectly sharp hot pixel like over here, and that's what made it pretty convincing to me that we had seen a very small moon of Pluto that nobody had seen before.
To be sure you've detected a real moon or planet, you have to show it's moving, unlike the background stars.
The thing that makes moons distinctive is if we come back later, they'd all have shifted because they all orbit the central planet. This required a great deal of patience to then wait about 6 days until we got our next set of observations of the Pluto system. Sure enough, the object was still there. It had moved by just about the right amount to be something orbiting Pluto, and we knew we had a moon.
Next year, Showalter and colleagues went back and built on lessons learned to see what else might be there. Summer 2012. Now, Mark had 15 more days of Hubble observations.
Now, what you can see here are 3 time steps. Each of those time steps is actually about 45 minutes of data. That means it's long enough that the little moons move. It's moving back and forth in this 3-frame sequence. Hydra is moving, Nix is moving. I mean, it doesn't take a rocket scientist to say that that looks like a little moon of Pluto. It's moving just the way the others are. They're all going around the planet in the same direction. And so it was just a couple of weeks later that we made the announcement that the fifth moon had been discovered.
Patience, persistence, ingenuity. That was exactly what led to the discovery of Pluto back in 1930. In Kansas in the 1920s, Clyde Tombaugh grew up in hard times and built telescopes using leftover farm implements. To check the accuracy of his best telescope, he sent drawings of Mars and Jupiter to the Lowell Observatory in Flagstaff, Arizona. They were looking for staff, and he was hired. Along with observing the stars, he stoked the furnace and shoveled snow. But one assignment made history. Day after day, he'd use this machine, known as a blink comparator, to look for anything in his images that moved. It was tedious, painstaking work, but on plates taken on January 23rd and 29th and analyzed in February, he saw a small dot that did move against the fixed stars. Announcing the results after careful confirmation, the observatory made it easy to find the new planet by adding arrows.
This is an incredible work of observational astronomy, and having done something similar but with much more powerful tools, I can really appreciate his achievement.
For decades, Pluto remained, more or less, a point of light. But in the mid-70s, Dale Cruikshank and colleagues attached cameras with infrared filters to a telescope at Kitt Peak.
Detectors or sensors had been improved, and larger telescopes had become available. Well, we did that work in 1976 and found evidence for frozen methane on Pluto's surface. It was several years later that we found the evidence for the other ices.
In 1978, astronomers Jim Christie and Bob Harrington analyzed new plates taken at the U.S. Naval Observatory in Flagstaff. Christie noted an elongation to the north of Pluto. 1 month later, the bump had disappeared. From this and other evidence, they concluded that Pluto, like Earth, had a moon, Charon. From eclipses between Pluto and Charon occurring in the 1980s, astronomers calculated that the moon was almost half the size of its parent body, so large that both objects spin around their mutual center of gravity, outside Pluto. Pluto and Charon were the first double dwarf planet combo discovered in our solar system. Using the basic physics of their orbits and the distance between them, astronomers could calculate their mass and size. Pluto was a little smaller than Earth's moon, about 1,500 miles in diameter, and had only 1/10 its mass. Between 1985 and 1990, astronomers were in luck. As Pluto and Charon orbited their mutual center of gravity, each passed in turn in front of the other. The so-called mutual events allowed astronomers like Mark Bowie to capture the changing patterns of light. Patiently, Bowie created a map of Pluto. Pluto turned out to have one of the two most contrasty surfaces in the entire solar system. In the mid-90s, Bowie and Alan Stern used the Hubble Space Telescope to make the first direct images of Pluto's surface.
And it's exciting to Mark and I and to our whole scientific team to be able to see this object that no humans really could glimpse as a real planet, as a real object in the solar system previously.
In 2005, Hal Weaver and Alan Stern used the Hubble for another close-up look at Pluto and Charon. They discovered two small, dim moons where only Charon had been seen before. Now we know from Mark Showalter's work that there are 2 more moons, making the current total of 5, and that Pluto is a genuine mini-planetary system. From its size and orbit, astronomers estimated that Pluto is perhaps 70% rock and 30% ice. That makes it one of the largest of a whole new class of objects, the ice dwarf planets, making up what's known as the Kuiper Belt. This region is named for Gerard Kuiper, a leading mid-20th century planetary astronomer. Kuiper suggested that the solar system didn't end with Neptune and Pluto, but that there should be a disk of other worlds beyond them. In 1992, from a mountaintop in Hawaii, David Jewett and Jane Liu found the first Kuiper Belt object. They were using new and highly sensitive CCDs, like the sensors in a modern digital camera. But their technique was essentially an updated version of Tombaugh's work. take carefully registered images of a patch of sky and see if anything moves against the distant stars. This one, QB1, did just that. It was only a few hundred kilometers across, 10 times smaller than Pluto, but still huge compared to a comet. Since then, teams of astronomers have found around 2,000 KBOs. Informed by cutting-edge astronomy, but with a fair dose of artistic license, let's take a trip through this third zone of our solar system.
We used to think of the solar system consisting of two different types of planets. The planets we call the terrestrial planets, which are Earth-like planets. That would be Mercury, Venus, Earth, and Mars.
Next out, the asteroid belt. Fragments of worlds smashed to pieces by gravitation and collisions. Then come the four gas giants. Jupiter and its moons. Saturn with its magnificent rings. Uranus, also ringed. And Neptune.
And then Pluto was this kind of, odd guy out. It was this little object at the edge of the solar system. And then when we found all these other Kuiper Belt objects, this is kind of almost a third type of object.
So for the first time ever, we'll be able to fly by a brand new object, an object that's been forming for billions of years, and understand what outer parts of the solar system are all about.
By July 2015, we'll know for sure what Pluto and its moons look like, and that will provide breakthrough information on all those other ice dwarf planets, the most numerous planetary objects in the entire solar system that make up the Kuiper Belt. Actually, the Kuiper Belt is more like a donut, bulging up above and down below the ecliptic where most of the planets move.
It's kind of like the asteroid belt, but much bigger. It has hundreds of times more objects in it than the asteroid belt.
Let's now visit 5 named KBOs in the exact positions they'll be in on July 14th, 2015, the day when New Horizons flies by Pluto. Quawa was one of the first Kuiper Belt objects discovered. It's about 1,000 kilometers in diameter, a reddish world, covered in water ice, methane, and ethane. And like many KBOs, it has a tiny moon of its own, Wayuut. Up above and down below the plane of the solar system, numerous KBOs have been flung about by Neptune's gravity. This region is known as the scattered disk. One of the largest of these KBOs, Eris, is close in size to Pluto and is made of rock and methane ice. Astronomers categorize KBOs by the tilt of their orbits relative to the plane of the solar system. And one of the more highly inclined orbits belongs to Makemake, named for a Hawaiian creation deity.
Some of these have methane or water ice on their surfaces. Some of them just seem to be covered in some brownish gunk. There are gray objects out there. There are brown objects out there. There seem to be distinct populations.
Some of them seem to be very spherical, and so they probably have warm interiors, and then others are peculiar shapes which suggest they're very cold and strong.
Perhaps the most bizarre and unexpected KBO is Haumea, a KBO shaped like an American football, made of rock and ice. It's white with red splotches and orbited by at least 2 moons. One of the strangest orbits of any KBO belongs to Sedna, discovered in 2003. Its orbit is the most eccentric of any KBO now known, bringing it as close as 76 AU to the Sun, but then carrying it outward to 936 times the Earth-Sun distance. Sedna's strange 11,000-year orbit seems to link it to an even vaster cloud of objects, ready for exploration by future generations. The Oort cloud is an immense icebox of long-period comets, from 10 to 100 times more distant than the Kuiper Belt, surrounding all the known worlds of our solar system.
There's a real record of the early history of the solar system out there in cold storage at the edge of the solar system.
This is what was left over. Pluto is the first member of that group.
But to begin humanity's exploration of the Kuiper Belt, you first have to get to Pluto. And that means getting a mission approved, a spacecraft designed and built, and delivered to the launch pad on time. And none of that was easy. 2015 may be the year of Pluto, but getting there has taken many long years of effort. And for New Horizons, there's a date when things got started: 1989. It was the year when George Herbert Walker Bush became president and the Berlin Wall fell. Far from Earth, it was also the year when NASA's Voyager spacecraft flew by Neptune and returned the first images of its moon, Triton. Hairstyles of some New Horizons scientists were very different, but for them, May 5th, 1989 was a most important date.
That's the day that I marched into the then Division Director for Planetary Science at NASA headquarters, Jeff Briggs, as a graduate student, and asked him why we aren't studying the mission to Pluto. And he responded, because no one's ever asked me before. That seems like a brilliant idea. Why don't we do that?
Space missions rely on hundreds, if not thousands of people, but sometimes it takes someone with passion and persistence to make things happen. And for New Horizons, that's Alan Stern.
I was interested in this when I was a boy, so I've been somewhere between in the groove and stuck in a rut for 40 years.
There'd been some thought about sending one of the twin Voyager spacecraft past Pluto to complete the exploration of the known solar system. But in the 70s, the scientific establishment wasn't convinced Pluto was all that interesting. Young grad students like Alan, Mark Bowie, and Fran Bagenal thought differently.
Back in, about late 1989 or so, there was a bunch of us who were really keen to go to Pluto.
And the thing that drew me to it the most was the fact that we knew so little. Here's the frontier.
So it was a bit of an opportunity for young people to come in and say, hey, where are we going to go next? What's the next great frontier that we should go explore? And it was clear, out to the Kuiper Belt.
Alan, Fran, Mark, and a small band of enthusiasts became known as the Pluto Underground.
So we realized to make this happen, we had to get together and campaign hard to make the case to go there and explore this little planet with all its moons.
All through the 90s, there were many competing plans for a Pluto mission, like the Pluto Fast Flyby, the Pluto Kuiper Express. A Pluto mission was on, then off, then on, then off.
If the Pluto mission had been a cat, it would have been dead long ago because they only get 9 lives. And we've had significantly more than 9 stoppages and odd twists and turns.
What finally turned the tide was the National Academy's Decadal Survey, a consensus document from leading planetary scientists that ranked a Kuiper Belt Pluto mission highest in priority for medium-class budgets. Finally, after competitive proposals were evaluated, New Horizons, which teamed Alan Stern with the Johns Hopkins Applied Physics Laboratory, APL, and several other institutions across the country, was selected by NASA on November 29, 2001. Now, plans on paper became metal in clean rooms. In 2004, lead scientist Alan Stern described the mission's key science objective.
Well, you know, the key to planetary science is that you really have to go places to get the resolution, to get up close enough to really see what's going on. We want to get up close and personal.
The very best resolution of current telescopes looking at Pluto would give this kind of fuzzy image of a much more familiar world. But here's what New Horizons would see if flying over New York City. Lakes in Central Park, wharves on the Hudson River.
New Horizons is the first really of a whole new breed of spacecraft that is focusing on a very specific task.
For this first mission to Pluto, the questions are basic. What do Pluto and Charon look like? What are they made of? How do their atmospheres behave?
We had to really be disciplined and say, we can't do everything. Let's focus on the primary questions and design the instruments to answer those primary questions.
The long-range imager, LORRI, will be used for navigation approaching Pluto and close-up views during the flyby. The wide-angle camera, Ralph, has both visible light and infrared sensors to map Pluto and Charon and characterize their icy surfaces. There are 2 fields and particles detectors to probe the solar wind at Pluto. The large radio antenna is an essential communications device, but both REX and ALICE, an ultraviolet imaging spectrometer, are part of experiments to analyze Pluto's atmosphere. And there's the Venetia Burney Student Dust Counter, built by undergrads at UC Boulder, and honoring the schoolgirl who named Pluto back in 1930. Together, the 7 science instruments comprise the most powerful set of detectors ever sent on a first flyby of any world in our solar system. But their innovative and highly miniaturized design means that even when all are operating, they draw less power than half a 60-watt bulb, and they're intended to work together seamlessly. After building comes testing, but always with an eye on the clock and the calendar.
It's very, very important that we launch in either 2006 or 2007. We have to make that deadline.
If you want to fly to Pluto on the quickest route, you need Jupiter in position. And that means we have to launch in January of 2006. It feels a little bit like being strapped to a train going 500 miles an hour.
The test program involves teams of engineers at Johns Hopkins APL and then at NASA's Goddard Space Flight Center.
Once we launch this, we can't go after it with a screwdriver. We can't go fix anything that isn't working.
We make sure that we carry plenty of spare equipment on board the spacecraft. If our main computer breaks, we have a backup. If our main transmitter breaks, we have a backup.
One of the things we do is we put the whole spacecraft on a gigantic vibration table, a paint shaker, and shake it. And then test it after that, and shake it again and test it again. So that's what we're doing from now until launch.
Along with testing the spacecraft, New Horizons needs to train and test its human operators. And for a mission planned to reach Pluto in 2015, it's important to have young people on board early, so they'll be around at close approach.
It's good that we can do that, so they will have both the time, the focus to stay with the mission over this long period of time.
Many of the faces you see around Mission Control in 2004 and 2005 are young and enthusiastic spacecraft engineers.
Normally we're focused on subsystems and instruments in the spacecraft surviving that duration, but for people we have to have a longevity plan.
They'd be committing the prime of their careers to this mission to Pluto, knowing they'd be a decade older when New Horizons reaches its primary target.
The ability to practice things in those years far out there are all part of the planning now to assure mission success then.
How old are you going to be?
In 2015? I don't know, somewhere in my 40s.
Oh, and you're a youngster.
Yes.
In late 2005, the action shifts to Cape Canaveral. New Horizons may be light and relatively small, but launching it to Pluto requires America's most powerful rocket, the Atlas V. New Horizons would be traveling so far from the sun that solar panels wouldn't be sufficient. So the Department of Energy delivered an RTG that would power the Pluto mission by turning heat from the radioactive decay of plutonium into electricity. Working round the clock, they arrive at Pad 41 before dawn. On behalf of NASA and the entire New Horizons team, Stern wanted to be the last to bid the spacecraft bon voyage before closing up the hatch. On January 19, 2006, after 17 years of planning, building, and testing, a picture-perfect launch that thrilled onlookers in Florida and the mission operations team back at Johns Hopkins in Maryland.
We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
Despite immense technical and timetable challenges, the mission had made its window and was on its way. New Horizons' velocity at launch was the fastest ever, traveling almost 60 times faster than a jetliner. In just 9 hours, it passed the orbit of the Moon. Apollo had taken almost 10 times that long. 1 year later, a slingshot gravity assist from the giant planet Jupiter provided another 2 kilometers per second boost, cutting travel time to Pluto by 3 full years. But this was more than just a jump in speed. The Jupiter flyby was a scientific dress rehearsal for Pluto. New Horizons instruments returned detailed images of Jupiter's clouds, moons, and rings.
We got the night shine. Oh, wow, look at that.
Then it was off across the empty ocean of space, with no new land in sight till Pluto in 2015. The spacecraft had been tested and passed with flying colors. Now it was time to test the humans and the ground systems. July 5th, 2013. It's day one of a 9-day encounter rehearsal.
The main success criteria for this rehearsal is for the spacecraft to flawlessly perform its activities as if it were at Pluto, with everything the same, except that Pluto's not there.
The dates in 2013 were carefully chosen so that Earth-received times would be identical to those for the real encounter in 2015. Mission managers wanted scientists and engineers to experience the stress of time-critical 24/7 operations expected for July 2015.
We're flying by an object that is a huge distance from Earth, and we're trying to hit a box that's 100 by 150 kilometers wide. And that then leads into maneuver planning and trajectory control needed to thread that needle and hit that small box. It's way the heck out there.
This rehearsal would actually be uploading commands to New Horizons to instruct the spacecraft to run through the exact same set of observations as in 2015.
There definitely is an element of risk involved, but from one standpoint, if you didn't do any simulation with the real spacecraft at all, you could argue that could pose more risk because you don't want such a critical activity only being done once on flight.
Those are all invaluable to get us ready and practiced for the one and only shot we'll have to explore the Pluto system.
We've been waiting 12 years since we wrote the proposals to do this rehearsal. It's the last big step before we can do the encounter.
We think that we are about 10 million miles out from Pluto and closing.
But so far, so good. We're off to the races. Today is our 2,724th day in flight. This has been a long time coming, literally. I only want to say thanks for all the work. Let them eat cake.
July 12th, 2013, standing in for July 14th, 2015. This is it, a minute-by-minute simulation of Encounter Day. It's make or break.
Well, it's the most important because we've just been spending the 24 hours of the most intense activities that we've been running on the spacecraft, and this is the longest that we've been out of contact since we've entered encounter rehearsal.
This may be a rehearsal, but New Horizons has been firing its thrusters and spinning in space, identical maneuvers to those planned for 2015. On Encounter Day, the spacecraft will be too busy taking data to send back images. That's why its first simple "I'm alive" message will be so important.
Sometime within the next minute, DSS 43 should lock up on the signal.
We're good. We're nominal. Spacecraft's nominal, and it looks like all the observations that we had planned between the last track and this track happened.
So this gives us good confidence that at least the spacecraft has been performing all of those twists and turns that we've been anticipating it to over the last 7 days.
I like to say that at the flyby, I don't want to be learning anything about the ground system or the spacecraft or the team. I want to be learning only about the Pluto system.
No spacecraft has ever been to Pluto, nor will ever go back in our lifetime.
Pluto is every child's favorite planet. You know, you ask anyone under the age of 6, and they're going to say Pluto.
We don't exactly know what Pluto looks like, but it looks very exciting from the images we have from the Hubble Space Telescope so far. We really can't wait to get there and see what it actually looks like. So if anybody says that Pluto is boring or not important, no way.
Before New Horizons arrives at Pluto, most everything we think we know about the planet and its moons is up for grabs.
Virtually every place we've sent a spacecraft on a first reconnaissance mission like this, that we find out that our Earth-based notions were flat wrong. So I'll tell you what we expect, but before anything, what we expect is to be surprised.
From the 1990s through today, Stern has been consistent in avoiding speculation.
You get the same answer everybody's gotten from me for almost 20 years. I don't make predictions. except for one. My best guess is we're going to find something wonderful.
But in the final months leading up to the July 2015 encounter, it's hard for most humans not to imagine what we'll see. Many planetary scientists, like Paul Schenck, base their expectations on what we saw when Voyager 2 reached Neptune, and specifically as it flew by its moon, Triton.
Voyager was a 10-year-long exploration of the outer solar system, and every time they got to a planet, it was basically the first time anybody had really seen those bodies. So when they got to Jupiter, they were greeted with enormous surprises. The erupting volcanoes on Io were just completely unexpected. And so when they got to Uranus, there were more surprises. The exotic trains of Miranda and Ariel, for example, were not expected. So by the time they got to Neptune, they were kind of accustomed to the idea that they were going to be surprised. And sure enough, Triton completely blew them away.
Bonnie Barati was at NASA's Jet Propulsion Lab as the first images of Triton, a moon of nearly 1,700 miles diameter, came down.
Triton was almost a twin of Pluto. It's about the same size, about the same brightness.
Originally, Triton was probably a Kuiper Belt object just like Pluto, floating around in space, but then it got too close to Neptune and it got captured by Neptune's gravitational field.
Recently, Paul Schenck enhanced the original Voyager data to create this detailed flyover of Triton.
It has odd patches and odd blob-like features, kind of like amoebas crawling around on the surface. Triton has very few impact craters. Its surface is extremely young geologically.
And it actually has geysers spurting material off into space.
Here is a body that is hundreds of degrees below zero. It's so cold, it's forlorn, it's barren. We just didn't expect to see this activity on Triton. It was quite a surprise.
If you just assume that Pluto was going to look exactly like Triton, which is the most similar object we know about, then you might expect to find a very interesting body.
But Triton is not the only dynamic ice world in the outer solar system. 16 years later, the Cassini spacecraft sent back images of Saturn's moon, Enceladus, about 300 miles across.
This is a tiny little moon, and Enceladus is actually a winter wonderland. It's very bright. It reflects almost all the radiation that falls on it, and it has these huge ice volcanoes spewing out from its south pole.
And Enceladus is continuously giving off puffs of water vapor, and so if you start to see puffs of water vapor coming off Pluto as New Horizons gets closer, that would be exceedingly interesting.
But what forces can power volcanoes in the deep freeze of the outer solar system?
Triton and Pluto are both balls of ice with presumably rock in the center, and so one of the sources of energy is radioactive decay inside the rock, which gives off heat just like the Earth is heated. If you just let Pluto sit there and pump the heat out of the rocks, you generate enough energy to melt a couple of 100 kilometers worth of ice. It's still possible to have an ocean beneath a relatively thick ice shell. The ice shell might be 100 miles thick or so. Over billions of years, the ice shell gets thicker and thicker and thicker as Pluto cools, and as it does so, it squeezes the water underneath, and if you squeeze the water too much, then it may well actually create fractures and the water could jet out to the surface.
When you're going out to the edge of the solar system, you kind of have to expect some surprises, and we're going to see them at Pluto as well.
Just as Triton and Enceladus were mere dots before spacecraft reached them, until now, Pluto has been an astronomer's planet. That's about to change.
We are going to start off as astronomers, and we'll be using astronomical tools to try and sharpen up our images and pull every last little bit of detail out of these fuzzy blobs. We gradually turn from astronomers into geologists as we get closer and it becomes a real world.
Jeff Moore was in the room at JPL as those Triton images came down, but he also enjoys field work and thinks we'll recognize some similar planetary processes at work on Pluto as back on Earth.
So I'm a geologist, and although we don't expect to see oceans on Pluto, there are common processes which operate on this planet, which are likely to operate also on Pluto and its moons.
While the scales are very different, erosion shapes landforms here on Earth and all across the solar system.
there are these little finger-like projections that are formed by the process of erosion, where wind and water have sculpted this landscape by taking advantage of small differences in the strength of the original rock, creating large, huge, fantastic landscapes, such as on Jupiter's moon Callisto, and we can anticipate that we may perhaps also see landscapes like this on Pluto and its moons.
Pluto's 248-year orbit is more eccentric than our solar system's terrestrial and gas giant planets, greatly varying its distance to the Sun. But it's typical of many other objects in the Kuiper Belt and newly discovered planets around other stars. That, plus its highly angled polar tilt, combine to produce strong seasonal effects.
In fact, the seasons of Pluto are amongst the most extreme of any seasons on any world that we know of orbiting the Sun.
And those extremes may be one reason why its surface is also extremely contrasty.
Pluto is perhaps the most intensely bright and dark place that we've seen in the solar system. This dark surface collects more heat. It warms up like asphalt does on a sunny day here on the Earth. And if there were frost that had settled on this dark surface, they're being heated up and driven off, and the transportation of this material could also be creating wind. So you might see small dunes oriented along the periphery of the dark surface, showing this process in action.
For planetary scientists, color can be a clue to the composition of surfaces that can't be sampled directly.
On the Earth, these kinds of colors from red to dark gray are generated entirely by the presence or absence of rust. On Pluto, we see also these same ranges of colors from gray to bright white to yellow to red to black, but there it must be due to a completely different process.
At NASA's Ames Research Center near San Francisco, longtime Pluto researcher Dale Cruikshank and postdoc Chris Matarese conduct experiments to see what processes might create the colors we see on Pluto, starting with gases like methane and nitrogen and the extreme low temperatures we know are found there.
In our cold chamber, we can produce a thin film of ice and then after that expose them to a beam of electrons, which are charged particles, comparable to what comes into Pluto's surface from space. We find that when we shine ultraviolet light or electrons on simple molecules, before too long the simple molecules are broken apart, and by natural processes they reassemble into more complex chemicals. So far, the colors we make in the lab from irradiating these ices is fairly close to what we see on Pluto. There are tones of yellow, light brown, up through fairly dark red. And if we carry the processing by ultraviolet light to an extreme degree, the material actually turns black. And this is almost the color of pure carbon.
Seeing how radiation transforms simple ices into complex and colorful organic molecules should help interpret the close-up views of Pluto's surface that'll be sent back by New Horizons.
Color translates to the duration of the exposure of these otherwise colorless ices over a year, 10,000 years, 10 million years. That may in turn tell us more about the nature of the exposure of Pluto's surface and even the age of Pluto's surface.
Dale Cruikshank began observing Pluto back in 1976. Now, 39 years later, he's ready for its close-up.
We can say that Pluto is chemically active, chemically dynamic. We don't know yet if it's geologically active and dynamic, but that's what New Horizons is going to tell us. We've been surprised in that way before as we've passed other planetary bodies that we had thought were totally cold, dead, inert worlds, and find that there are geysers, there are ice flows, there are cracks, and all kinds of evidence for geological activity.
I can still remember the first time I saw Pluto in a telescope, and it was just a little dot that you could barely see. It will be amazing that within a period of hours it will be transformed from this tiny dot that I studied as an astronomer to this huge geologic world that we'll be able to see volcanoes and faults and ices and mountains and craters. I mean, it'll be truly an amazing experience to see it transformed.
So, from sophisticated lab experiments, from exploring other worlds, and from applying insights from terrestrial processes, what should we expect when we get to Pluto in July 2015?
But the only thing that would surprise me would be if we turned out not to be surprised.
But enjoying the scientific surprises to come means avoiding dangers on the last few million miles to Pluto. That's next. December 6, 2014. In Mission Control, Alice Bowman and her team wait to get confirmation that New Horizons has exited what's called hibernation. For 2/3 of its 3 billion-mile journey, most spacecraft systems have been turned off, saving wear and tear on the science instruments. New Horizons sends a simple signal once a week just to say, I'm still A-OK. Alice's team has a unique way of showing spacecraft status. When New Horizons is hibernating, their bear mascot is safely asleep. When the spacecraft wakes up, they put on its party hat. If all goes well, this will be the 18th time spacecraft and bear have woken up. But December 2014 is different. VIPs from NASA are on hand. 2 film crews document the action as Alan explains the benefits of hibernation.
It lowers our cost because we don't need to have people babysitting the spacecraft 24/7.
Outside interest in New Horizons is building. If all goes well, New Horizons will stay awake, flying by Pluto in July 2015, and then returning data until October 2016.
Copy that. Thank you, GNCs.
Tonight, data trickles in, and Alice has to wait to be certain New Horizons is fully awake.
We should be getting it momentarily.
Should be any minute now.
It's like watching paint dry. I figure if I stare at the screen hard enough.
And packet 5 just came in. There we go.
PI, PM, Mom on Pluto 1. We have a nominal wake-up of the New Horizons spacecraft on its way to Pluto. We're ready for our next leg of the journey.
Was awake.
Our bear. He's going to be here for a while.
This is a watershed day. We have completed the cruise across 3 billion miles of space. The spacecraft is now awake.
Finally, after 9 years, I'm glad to see hibernation behind us and active ops ahead. On to Pluto.
But there are still hundreds of tasks to ensure a safe flyby in July 2015. January 27th, New Horizons has been sending back technical data and all seems fine. But today is the first time Hal Weaver and Andy Cheng will be seeing new science images.
I saw it pop up here. Yeah, let's try that again.
Cheng is lead scientist for the LORRI camera.
LORRI is used for navigation to find the targets and to correct the trajectory so we get to the right place at the right time.
Voltages, currents, temperatures all look normal. No error messages.
This is it. Now let's check out the very first images. And then Sharon, right there, peak pixel 55. That's right. Okay. All right, so there they are. Let's look at the whole.
For project scientist Hal Weaver, even the jump in size from 1 to 2 pixels was significant.
This is a real milestone in the New Horizons mission, the very first images of Pluto in the Pluto encounter year. Hadn't turned LORRI on, hadn't gotten any images since last summer, last July, but this is it. This is the start of it. How she blows.
We really don't know what we're going to see. That's what this mission is all about. What is the surface of Pluto really like? How big is it? What are the orbits really? So it's nothing but delightful surprises coming for us.
But some of the surprises may not be quite so welcome. As New Horizons gets still closer to the Pluto system, LORRI will be able to identify small moons and possible rings that can't be seen from Earth. John Spencer is leading the UHAZ campaign. UHAZ stands for Unknown Hazards.
We may find new moons or even rings around Pluto, and if we see anything like that, we're going to want to determine whether it poses a threat to the spacecraft, because if it does, if there's debris that we might run into that might damage or kill the spacecraft, then we want to evaluate that hazard and determine whether we should take any evasive action.
To find out just how vulnerable New Horizons might be to even tiny dust particles, the mission sent samples of spacecraft components to the White Sands test range. Technicians at White Sands set up gun tests to assess how vulnerable New Horizons' outer covers and cables might be.
We went to 2 facilities that could shoot things into parts, models of the spacecraft.
While the results might look dangerous, the mission has options to take evasive action.
One of the backup strategies we have if we feel we need to give the spacecraft extra protection is that we orient it so that the high-gain antenna here, which is literally pretty bulletproof and can protect the spacecraft, is going to be facing forward in the ram direction. This is ram in the sense of battering ram. It's a direction in which stuff will be coming at us and ramming into the spacecraft. And if that is facing forward, then any dust particles that hit the spacecraft are most likely to hit that antenna where they won't cause us problems, and only a small part of the spacecraft around the edges is going to be exposed to those particles.
That would protect the guts of the spacecraft, but limit the pointing of the cameras.
The cameras are fixed to the spacecraft, so if the spacecraft has to point in one direction, the cameras can only point in a limited range of directions. This limits the amount of times we can photograph the system as we go past, because we can only photograph objects when they're just in the right angle that we can look at them while protecting the spacecraft with the main antenna.
Another option is to take different trajectories through the Pluto system. That's called the Shabbat play.
Shabbat is the best acronym in the space business. It stands for Safe Haven by Other Trajectory. And it is the word we use to represent our backup plans at Pluto. The second Shabbat takes us much closer to Pluto, into the region where atmospheric drag depletes orbits of any debris, which we think would be the safest Hail Mary pass that we could fly if we have to do something different than the nominal. We are coming into the Pluto system with the ability, if we learn something we don't expect, to be able to make a change and get the goods.
But those decisions can only be made in the last month before closest approach, and there'll be limited time to evaluate the best options. So in February 2015, Spencer's UHAS team, including ring specialist Mark Showalter and postdoc Simon Porter, are running through a readiness test. Now they're on the clock and being scored for whether they can work through the calculations fast enough to decide on a trajectory correction maneuver that might prevent loss of mission. And that makes this exercise more critical than any that have gone before.
The difference between this and previous operational readiness tests is that this is where we have to demonstrate to the project and NASA that we can do this.
But the only test that really matters comes on July 14th, 2015. That one day will pay off 26 years of dreams and 9 years in flight. For the science team, the year of Pluto began with another meeting to review the latest data on the Pluto system and to hear updates on how the spacecraft was performing. Mission manager Glenn Fountain, who'd been with the project from its start, summarized remaining risks. Red boxes are possibilities that could kill the mission. But now, in 2015, there are more and more green boxes, risks that have been minimized.
Something that we haven't thought of still might happen, but I'm confident that whatever happens, whatever fate throws at us, this team will be able to resolve it, and we'll go on to get wonderful data when we get to Pluto.
We have a fantastically talented team of people who have worked very hard, and we've tested the sequences inside and out. And while there are always unknown unknowns, I'm very confident and really looking forward to the curtain rising.
Along with mind-bending technical details, there also was a sense of history in the making. To document the long years of effort to get this close to Pluto, the mission recreated a team photograph taken in 2004. As Glenn, Alan, and Alice had carefully planned back then, many of the scientists and engineers were still actively engaged in New Horizons and looking forward to July 2015.
We have worked hard to get a coherent team, because if you don't have a good team to operate the spacecraft, to do the planning, you will fail. And so we worked a plan early in the mission to have younger people with the right amount of experience to be on the mission. And it's just like watching your kids grow. It's like all of a sudden, where did the time go? You know, they are older, they're more mature, and they're now the very experienced veterans.
But the hard work of mission planning was by no means over, even this close to Encounter Day. While exploring Pluto in 2015 is exciting in itself, New Horizons was recommended in part as a mission that might continue on, farther out into the Kuiper Belt. That takes identifying potential targets now for a still more distant flyby, should NASA approve an extended mission. This challenging task was assigned to John Spencer, Mark Bowie, and a team of young postdocs. And like everything else about this mission, it wasn't easy. Bowie and John Spencer had been using Earth's largest telescopes in Hawaii and Chile, but even Earth's best couldn't crack this task.
But the basic problem is the Earth's atmosphere is just a mess at these scales. There's a limit. And that's what we've been beating our heads against. Now with time running out, we had to turn to Hubble. And so we sort of, not so jokingly, talk about Hubble to the rescue. Without Hubble, we would not have these objects.
Mark and his young collaborators came up with innovative search techniques using custom software.
What that does is makes the stars smear out and makes the Kuiper Belt objects hold still.
It's been a lot of work, but to do something as exciting as this has been just so much fun. I've been plugging through the data today because it's fresh data, and I just really, really wanted to know what the answer was.
Well, we would have been in big trouble if we didn't find the KBO in time. So there was this pressure, but honestly, we had the best people in the world working on the problem, and we did it.
And we just do the math, write the software, crunch the pixels, and then I create this graphic, and from that point on, it's what I call wetware. It's what you got in your head.
In reality, KBOs are moving against the fixed stars. Mark came up with a way of making them more obvious by flipping that around and making the stars appear to move, and any KBOs stand still.
Right in the middle, there's something that's just holding dead constant. And that's the Kuiper Belt object. You can't argue with that.
It was a high-tech variant of the approach that had been instrumental in exploring the Pluto system right from the start.
But at the core, it's a technique that hasn't really changed since Tombaugh's day. You have two pictures of the sky taken at different times, and you're looking for the stuff that moves. As soon as you see something real, there is absolutely no question about it. As soon as it flashes on the screen in just a millisecond, there it is, it's real, and you know, I've found another Kuiper Belt object.
But finding a KBO is only half the battle. Is it located where New Horizons can reach it with available fuel?
Once you have the orbit, and we know where the spacecraft is and where it's going to be, we can figure out how much fuel the spacecraft is going to need to use to get to these objects.
With more Hubble time, New Horizons got a pleasant surprise.
It looked like we might actually have to burn the engines to miss the object, which was a pretty exciting concept. You know, it's a good thing we looked, because you wouldn't want to run into one of these things.
These cold classicals, they're pretty much as they were 4.5 billion years ago. They're little fossils. That's incredible. We have no idea what they're going to look like.
So with potential targets found at last, it was on to Pluto.
I'm feeling pretty exhilarated at this point. You know, you're at the top of the roller coaster, you're about to go down that dizzying, thrilling ride into the system. Just seeing Pluto there getting bigger and bigger, it gives me goosebumps.
Today, we're only a few months away from the encounter. We're less than an astronomical unit, the distance between the Earth and the Sun, that distance away from this fascinating object. It's the last major body in our solar system that we really need to visit.
To be putting the capstone on the initial reconnaissance of the solar system, it's heartwarming, and it feels like something that makes a career worthwhile.
As spacecraft goes, New Horizons is a very small team, but still, we've been working on this for over a decade, and you add it all up, and it's about 2.5 million work hours to get ourselves to Pluto.
We have waited first the 4 years that we couldn't hardly think about because we were running so fast, and then it is, oh, we wait, and now we are ready to begin the encounter. We have had delayed gratification.
The year of Pluto is, simultaneously a beginning and an ending. It's an ending in that we are completing our objective. We're accomplishing the flyby of the Pluto system for the first time. But it's also the beginning of a whole new chapter for science, of really being able to explore these objects as the data comes down over a period of months. In bringing in postdocs and the younger scientists who, some of whom were in high school when we started this project, and now they have their PhDs and they are spectacular experts and very talented at what they do.
I was in preschool when Alan first started talking about a Pluto mission, and finishing high school and starting college when it was built, and in grad school for the cruise.
Having young people come into these programs, gaining the experience, they're going to be the next generation of explorers.
We've never been to a KBO. We've never been anywhere close to a KBO. This is the most unexplored area of the entire solar system, which is another way of saying this is the most unknown area that we as humans can